Good morning, everyone, and welcome to this day of talks. So I'm told by the organizers that we have to finish things on time so that all of you can go to Konark on time, okay, and have a lot of time to see those things too. So let's start. And the first speaker of this morning is Liam McAllister from Cornell, and he will be telling us about candidate decision vector. Liam.
Thanks. Am I on? Yeah. Okay. So it's an absolute delight to be back in India and back at an ISM. My first was in 2004 in Khajuraho. Very fond memories of that, and it's great to see how much the Indian string theory community has grown since then. So thanks so much to the organizers for all the hard work of putting this program together and giving me a chance to speak. So I'll be talking about a work that appeared last year with Jakob Moritz, which is now each of them was a postdoc to me at some point. Jakob is now faculty in Wisconsin. Richard is a postdoc at MIT, and Andreas is still a postdoc with me. And this work built on a lot of developments, in particular in collaboration with my former students. Where's the light? Okay. Mehmet Demirtas, Manki Kim, and Andres Rios-Tascon. And I should particularly highlight Manki Kim's role in spearheading an ongoing research program in using string field theory to develop a stronger foundation for the works that I'll tell you about. But I'm just going to talk about the already published papers now so that I can tell a relatively clean and slightly simple story. So here's the maximal goal of this line of work is to try to understand cosmology in quantum gravity. And we'd like to find solutions of string theory that describe our universe. The towering problem in this context is the cosmological constant problem, which is that the observed vacuum energy is absurdly small in Planck units. And although this is the problem that we'd like to tackle, I think it's too hard. And we won't be directly trying to address this problem. Instead, we'll take a slight turn and try to solve a supersymmetric version of the cosmological constant problem. Namely, we're going to ask, could we explain, could we understand a vacuum energy that's exponentially small compared to the cutoff scale, but negative in a supersymmetric vacuum? So can we explain how an exponentially large cosmology can arise from a theory with a much smaller fundamental scale? This is exactly the notion of scale separation that Tim told us about a few days ago. And if we succeed in this, which we will, we're going to try to use such supersymmetric solutions as a foundation for constructing necessarily non-supersymmetric solutions that are de Sitter vacuum. So that's the goal. So our current, less maximal goal is to construct de Sitter vacuum of string theory. And we're going to try to do this in totally explicit compactifications, and importantly with quantified errors. And so the goal, although we won't completely succeed, is to build fully realized toy models of cosmology and quantum gravity, which we can then ask many things about how de Sitter quantum gravity works. So what have we actually done? We've constructed candidate de Sitter vacua in totally explicit compactification. This is following lines laid out by Sandeep et al. More than 20 years ago in the famous KKLT paper. And what you're looking at here is, this function is the scalar potential of a four-dimensional theory coming from a Calabi-Yau flux compactification versus the Calabi-Yau volume in string units. And what I call your attention to is for the pink line, de Sitter, the minimum, the local metastable minimum of the potential has positive value of vacuum. So that's a de Sitter vacuum of the effective theory. So the purpose of the talk is to explain how this came about. So a slightly broader view of the result that I'll be describing is we construct a corner of the landscape of flux vacua on Calabi-Yau threefolds. And in that setting, we explicitly compute the four-dimensional effective field theory at leading order. And I'll be quite explicit later about what I mean by leading order, but roughly you should think of it as leading order in G string and alpha prime, but including certain known non-perturbative effects. And in that EFT, we exhibit metastable de Sitter vacuum. So the solutions I described for you they really are de Sitter vacua of the EFT that I construct. We called the paper candidate de Sitter vacua because I can't prove to you today that the EFT that I've constructed is a close enough approximation to the real exact theory that comes from the string compactification. That's what the approximations are for, trying to get our hands on a sufficiently accurate EFT. So I'll produce for you an EFT that has a de Sitter vacuum, and I'll argue that it quite plausibly is a good approximation to the truth. Okay, but further work is going to be required to quantify errors, and that's an area for subsequent publications. So plan of the talk, I'm going to try to give a gentle and broad overview to the context of this kind of problem, although Tim gave us a great overall picture already, so I won't say quite as much. And then the main mechanism that I'll describe is a way of getting a small superpotential. So I'll explain how to do that. And then having done that, I'll be able to tell you about de Sitter vacuum. Okay, so to start out, we're going to consider compactification of type 2B string theory on a Calabi-Yau threefold. Throughout this talk, we'll have a threefold and its mirror. The threefold where we put type 2B is called X. And this compactification is a 4D theory with n equals 2 supersymmetry that has some number of vector multiplets, some number of hypermultiplets counted by Hodge numbers. But it's an n equals 2 theory. It has an exact moduli space. And an exact moduli space means there's many massless scalar fields in 4D, and that's definitely not possible in cosmology. It's incompatible with, for example, Big Bang nucleosynthesis, fifth-fourth tests, and more besides. But there's a related solution. Rather than solving the vacuum Einstein equations, with the only term appearing in the Einstein equation being the vanishing Ricci curvature of the compactification, we could try to solve the non-vacuum Einstein equations. Namely, we could include sources of stress energy. And those sources of stress energy in this setting will be d-branes, orientifold planes, and flux. And although all of them are essential, the compactifications are called flux. But you should really think of them as just non-vacuum solutions that have all manner of sources. And so such a flux compactification can preserve less SUSY. It can preserve n equals 1 or n equals 0 in 4 dimensions. I should say all the cosmology, everything I'm talking about today is going to be in 4 dimensions. We're going from 10 to 4, no toy cosmologies in other dimensions today. And the classical effect of the fluxes and then additional quantum effects from instantons induce a potential for the moduli. So I'll denote the moduli by little phi. There's a number of them that will come to discuss. And a point in the moduli space phi star where the potential has vanishing derivative and positive Hessian is a vacuum. And if the value of the potential at that vacuum is positive, we call it a de Sitter vacuum. So it's as simple as that. The thing that's complicated is we have to compute the potential V in flux compactifications and figure out whether it actually has de Sitter vacuum. That's where the work is. Okay, and this involves computing a lot of things. Over the course of this talk, I'll explain each of these things that we have to compute, but maybe I'll lay them out now. We're going to have to compute the potential from fluxes. That involves doing certain period intervals and solving a Diophantine problem in the flux form. We're going to have to compute world-sheet instanton terms and superpotentials from Euclidean equations. And then when we've done all that computation, we'll have an effective theory. And with that effective theory, we're going to have to look at it and find local minima, or see if there aren't any. And now, I think an important takeaway, if you say, what's the point of not interested in KPLP vacua, or maybe you think that there's going to be something wrong with one of these, quite possible, but the takeaway can be that even if the specific vacua that we find turn out to disappear upon including currently unknown quantum corrections, the general technology we're describing for building parts of the landscape can be used for many other things. So we're basically building tools. Okay, so what, yes, please. Absolutely, yeah, thanks. And I will give you even a budget for these by the end of the talk. So to sketch it, it will turn out that everything I need to know about the superpotential I can come to know by working hard enough, and some things about the Kähler potential that I would like to know I cannot. And so the most dangerous corrections will turn out to be one string loop corrections to the Kähler potential, and alpha prime corrections to the action for an anti-D3 ring. And I'll describe in detail where those come in. So one is in the string expansion, one's in the alpha. Great, other questions? So when I say now unknown, what I mean is I can certainly write for you what the terms ought to be in principle, but often one can't compute the coefficients. And that's a task for future work. And so what we're going to try and do is exhibit vacua, control them, argue that they exist, without knowing certain higher order corrections. And we'll get relatively far via a strategy that I'll describe. Okay, so to understand the strategy, let's remember that an n equals 1 theory is described by a superpotential and a Kähler potential. And the superpotential is a holomorphic function of the moduli. Killer potential is not, it's an analytic function. Depends on phi and phi bar. And so correspondingly, the superpotential is protected by non-normalization theorems. And it's ultimately largely determined by topological data. And so the superpotential is knowable. I will show you it takes a lot of work to compute it in some cases, but it can be computed with, let's say, purely computational geometry, not doing Feynman integrals or, for example, working out moduli spaces or Riemann surfaces or something. But K will require more physical work, and it's poorly understood beyond one loop. So if you decompose W to K, we understand both the tree level part and the non-perturbative part of W. There are no perturbative fractions by non-perturbative. And in K, we're going to live with mostly the tree level part. We don't know much about the rest. But the scalar potential is determined by both. This is the famous F-term potential in an N=1 theory. And so you might say, well, if you know W but don't know K very well, how can you make any progress? And that's where the strategy comes in. We're going to preserve as much SUSY as possible for as long as possible. And we're going to pick a setting where the vacuum structure is dominated by superpotential terms that are going to be dictated by integer data that we can choose or compute by Calabi-Yau topology and by flux integers that I can pick. I'm also going to choose a setting where the number of vacua is practically unlimited, by which I mean if my students go and look and they find some vacua and I find the vacua unsatisfactory, I can hire a new student, and the new student will have a search space to go into where there are better vacua. We won't run through the whole set of possibilities. And our basic operation is to develop computational geometry software to obtain the superpotential systematically by combinatorial operation. So I won't say really anything about how the software works. What I will say is, hiding behind all of this, I say combinatorial, and you might have thought, what's combinatorial in studying Calabi-Yau threefolds? Well, behind the scenes, the Calabi-Yau threefolds are hypersurfaces in toric varieties, and toric varieties are sort of tinker toy kinds of constructions of algebraic varieties that you can understand and operate on combinatorially, and that's where some of the efficiency comes from. But I will hide all of that behind the curtain for this talk, unless there are questions. Okay, and then this top part is sort of a strategy for how might we deal with our lack of knowledge. This is how we're going to make progress and push forward. And then what's the physics idea that leads to the vacua? We're going to find cases where competing exponentials govern the vacuum structure. And if the only things that are competing to make a vacuum are exponentials, then if you have a vacuum at all, it's going to have exponentially small vacuum energy. And maybe you won't find a vacuum, but if you do find one, it will be exponentially small vacuum energy. That's the game. Yes? Yeah, good. Yeah, good. So concretely what I mean is that there are particular contributions, so that the moduli potential, the potential for various of the moduli is controlled by superpotential terms that are computable in a regime of parameters where, when you evaluate the naive dimensional analysis estimates for the size of corrections to the Kähler potential, they're very subleading. And so this is not anything novel to us. I mean, this is actually buried in, I think, the part of the key insight of the KKLT paper. Look in a regime where you can try to self-consistently ignore corrections to the Kähler potential and see if that regime is actually workable. And so the longer answer, which we'll come to, is the control parameter ends up being the smallness of the flux superpotential, and that will allow us to find stabilization at a place where the volumes are relatively big, the couplings are relatively weak. And so we're not claiming to find the sort of generic vacua of these kinds of Calabi-Yaus with generic fluxes. We're trying to find the ones that are knowable. And so that's where that comes in. Yeah, thanks. Other questions? Okay, so why is this happening now? The basic answer I would give is the Calabi-Yau threefold examples that are accessible with pen and paper by classic methods, by strong individuals, are just too limited for making de Sitter vacua, at least of KKLT type, but I would argue more generally. And the reason, Buso and Polchinski taught us long ago that the landscape is complicated because there are a lot of choices of fluxes and topology. So if you want to have enough richness to find interesting cosmological solutions, you'd better have very finely graded dials. You'd have to have a lot of choices of topology, for example. That means you have to have many moduli. And that means all your computations are going to be in high-dimensional moduli spaces, which are not really suitable for analytic work. And that's why we're doing this in a computational way. And the computational geometry of Calabi threefolds has advanced such that these cases are in reach. That's why I'm giving this talk now. And I should stress, so far, this has nothing to do with AI or Moore's law. Right now, we just decided to develop algorithms that are adapting to the problem. I'm sure the time will come when both of these things contribute importantly, but the things I'm telling you about don't rely on that yet. Okay, so we've developed technology to do this class of computations, to compute EFTs. We've written a lot of papers about this, and all of our capabilities are put together in our software package, CY tools. So if you get bored during the talk, you can just download the code and mess around. Yes, please. No, you go to that page, cy.tools, and then install it. And if you have trouble with the install, let me know, and I'll tell my students, and they'll help. Yeah, we're trying to grow the user base so that more people do string compactification computations in a framework where we can share results rather than having to tech up the answers and say what our conventions are. You can share a notebook. So I think this is actually going to be quite helpful, far beyond the kinds of vacuum. Yeah. There's C also, but yeah, it's a Python front end. Just open a Jupyter notebook and then mess around. Yeah, but then the stuff that's most demanding, it's written. But you don't have to do particularly any high-level stuff to operate. Great. Other questions? Yeah, and if people are curious about this, please come find me afterward. I'll be happy to talk you through it. It's really capable at computing. Well, I'll show you. Pretty much anything you might want except metrics in Calabi hypersurfaces and torus varieties. Okay, so one thing you might want to compute, think back to mirror symmetry, periods, you might want to compute the integral of the 3-0 form of the Calabi over 3 structures. These are the basic coordinates on the model. And they'll play a big role for us. And it's been known for a long time how to do this. Hosono, Clem, Theisen, and Yao laid out an algorithm that works great in hypersurfaces, and Clem and Kreutzer prepared the instanton package that can do this computation in cases with numbers of moduli like 3, 4, 5, maybe 10 if you push it. But the cases we'll need will have hundreds and hundreds of moduli. And our contribution to this particular corner is just an information that's fast enough to handle the general case. And I won't tell you anything about how that was made to work, but it works. And now we can access anything in the Kreutzer-Skarka list up to H21 of 491. So this is, if you think back to the classic mirror symmetry papers, the original mirror symmetry pair, and then 2-parameter models, and then things sort of tapered off. These are 491 parameter models that we say. Okay, so now, please bear with me for 2 difficult slides in which I introduce all of the notations to tell you the story of what's going to happen. And then we'll be back to a slightly higher level discussion. Okay, so we're working with type 2B on a Calabi threefold. The moduli here are the axiodilaton, whose imaginary part is 1 over G string. The complex structure moduli, so I'll do that by Z, and the Kähler moduli, which measure 4 cycle volumes. And you can hold in your head that there's going to be 5 or 10 complex structure moduli and 100 or 200 Kähler moduli. Okay, so we're going to work with quantized 3-form fluxes here, and we'll make this complex linear combination. And you can just dimensionally reduce the 10-dimensional type 2B action. You find the flux potential looks like this at the classical level. And that can be rewritten famously in terms of a superpotential, Gukov-Vafa-Witten superpotential, which is either, you can think of it as G wedge omega, or you can write that naturally enough as a pairing of pi, the vector of periods, with G, because pi is the integrals of omega. The pairings with some symplectic matrix, but whatever. Okay, so that's the start. Now we have to talk about the n equals 2 structure for a minute. So we've got some 3 cycles. Let's make a basis of A and B cycles, a symplectic basis of 3 cycles in our space. And the periods, the integrals of omega over the B cycles and the A cycles, correspond to coordinates on the moduli space, the is these, and derivatives of the prepotential with respect to those coordinates. And so there's sort of a triad here, the prepotential, the coordinates, and the periods. Near large complex structure, which is a special point in moduli space that's nearer to large volume, and where we're going to be working, the prepotential splits into 2 pieces, a polynomial part and an instanton part. And this is actually very important for us. And so first, let me tell you about the polynomial part. The polynomial part, it's some cubic polynomial. I write this so it becomes hopefully clear that it's totally explicit. It's just some cubic polynomial whose coefficients, written in color, are known. section numbers, Turing classes, blah, blah, blah. We won't operate with it very much, but it's just some concrete cubic. And then the instanton piece. So the instanton piece we're going to need very much, and let me tell you about that. So the instanton part of the prepotential is a sum. Here Q is sum over curves, and means the Mori cone. So the cone of effective curves in the mirror manifold, so summing over curves in the mirror. The genus 0, the Bhubaneswar invariant of the curve, so counting some BPS index relation to the curve, by logarithm, I'm here, of exponential of the curve class dot the complex. So this is sort of horrible, but the way you can parse it is the instanton prepotential is the sum of integer prefactors that are knowable times exponentials, and the exponentials involve a complex. Okay, so sum of exponentials. Okay, so that's the end of the horrible stuff. Yes, please. Yes. Yeah, very good. Thanks. So Q is it lives in, it's a H21 dimensional vector, and but importantly, yeah, thank you so much. It's H21 of X tilde dimensional vector. So these things live in the mirror, and we're summing over all effective curves in the mirror. So if you were just doing like type 2A on a Calabi-Yau and counting curves, you would be summing over all holomorphic curve classes and with GW or GV invariants depending on your taste. And that's what I'm doing here, but I'm doing it. Yeah, thanks. The reason is that what I'm writing is the prepotential for the vector multiplet moduli space of type 2B on X, which is, yeah, that's right. Well, in fact, we're going to be doing the same computation on both sides, but right now we're doing it on the complex rate. Yeah. Okay. And so now the superpotential and prepotential are related, and so just as the prepotential decomposes into a polynomial and an instanton piece with a few algebraic sets that all vary, you can split the superpotential into a polynomial and an instantonic piece. Yes? Yeah, correct. So yeah, so indeed this is notationally bad. So let's go to the mirror of our threefold. The mirror of our threefold has H11 of X tilde is H21 plus 1 of X. And now when I have an H11 of X tilde dimensional cone, the Mori cone, and then intersect that with the lattice, and all the sites in the cone are the sites that I wish to sum. Did that address the question? Yeah, sorry about that. I think I probably should have denoted this, maybe put a tilde over the Q. But right, so I'm summing over, let's just switch everything over to the mirror, and I'm now summing over all holomorphic. Yes? The axiodileton. Yeah. The axiodileton, since in the axiodileton, as you know, lives in a hypermultiplet. And so right now on the vector multiplet side, we only have H21 of X or H11 of X tilde and anything. Okay. And so the reason that I'm troubling you with all of this stuff about the prepotential is the splitting into poly and instanton. That drives everything. That's going to be responsible for the core mechanism I'll use. So what I would hope you can take away from this is that just as the prepotential splits, the superpotential or the periods that are obtained from it split into a polynomial part and an instanton part. And now here comes the idea. Yes, sure.
Prepotential is something constructed.
Yeah.
Then you added the superpotential to make it empty.
Yes.
So why are
Yeah, very good. They're related because how do you compute the flux superpotential? If I give you some G, G is a complex linear combination of quantized preforms, okay, of integral preforms, you just integrate it wedge omega, but you can also write that as first integrate omega and also integrate G and dot them with a simplicity. But that means that if you know the periods and you've chosen the fluxes, you know the superpotential. But the periods can be known from the prepotential this way. That's why. So the prepotential is just an encoding of the periods, if I wanted to, I could have never said the word prepotential and just said, well, suppose I can compute the period split into polynomial instantonic. Okay? And an important point here is, okay, we switched over to the mirror in answer to some questions. This is the vector multiplet moduli space of type 2D. It's classically exact. The things that I'm calling instantonic, you can call them instantons on type 2A. But here, these are just exponentials that show up in doing a classical period. Okay? Okay, so because W splits, now here comes really the only idea other than strategy at this part of the talk. We're going to choose fluxes such that the first term is 0. So I know what these things are, principle, so I can try to solve this. But choosing fluxes means choosing integers, so I'm trying to solve some Diophantine problem. But if I succeed, it will turn out that the superpotential will then vanish along a one-dimensional locus in the complex space. And let me repeat that. This is the key result. If I succeed in finding fluxes for which the polynomial part of the period dot with the flux is 0, then all that remains is instanton. And the flux superpotential in such a direction is just a sum of okay. Now, I'm going to use the terminology PFV, perturbatively flat vacuum, for a vacuum in which the polynomial stuff is gone. And let me just put this in very zoomed out terms, what's going on here. If you think back to like Buso-Polchinski type arguments for the vacuum energy, there was a lot of fine-tuning required in finding small vacuum energy in that setting, because you were fine-tuning a huge number of order 1 things against each other. We are wiping out the order 1 things immediately by solving this Diophantine that I'm suppressing. And well, all that remains are instantons. So that's how we get into the game of small superpotentials. Okay, so that was the idea. And so now, let me tell you something general about exponential superpotentials. This is now, doesn't have to be in this particular setting. Suppose, just an old idea, the rate graph. If I have a superpotential, it's a function of one complex field C, that's, let's say, 2 decaying exponential. Then a straightforward calculus problem is just to minimize this superpotential along the the positive real axis, let's say. And if you do that and evaluates the superpotential at the minimum, you find this expression, which involves the prefactors and the exponent. And the point is simply that if the prefactors are slightly hierarchical and the exponents are close to each other but not exactly the same, then this is a big exponent and this is a small number, and the superpotential is distant.
To a particular class of Calabi manifolds?
Yeah, very good. So I didn't explain that. It turns out that most Calabi-out threefolds that we've ever studied do have the property that they admit some choices of fluxes that have a PFV. When we first started doing this work, I thought that this was a big ask, and now I don't think so anymore. Most Calabi-outs have PFVs, and many of the ones that have PFVs, you just open your laptop and they just come boiling out, millions of them. So they're quite prevalent, actually. Even though, sort of solving a Diophantine in high enough dimension is hard, but in low enough dimension where you can brute force parts of it, it turns out that there are big families of them. So, great. Other questions? Okay. So, yes, please. The particular fluxes that I'm choosing?
Yeah, but because they don't seem to be supported on devices, etc. If you taking the polynomial to be say,
freeform fluxes.
Yeah.
So they're describable as integral freeform. So they're elements of H upper 3 of X. See, was that
no, I was asking whether this can be thought of as bundles based on cycles on the devices.
based on divisors? No.
Yeah.
So
Because polynomial part is taken to be 0, so I guess the divisors are out.
So the thing that I'm getting rid of here are things that have polynomial dependence on the complex structure model. But these things, the fluxes that I'm talking about here, they live on 3 cycles in X. They spread 3 cycles in X. They have 3 forms in X. So they don't have an immediately natural relation to even dimensional classes.
I see.
We will do many things with even dimensional classes on X, but the fluxes live in.
I see. Okay, thank you.
need such an argument, and the reason is that generically, although we will talk about exceptions, generically, this isn't zero. So, I mean, it would certainly be a story where the R symmetry is spontaneously broken by world-sheet instantons on the mirror. I haven't seen such a. It's an interesting remark, actually, but I don't know how to do it that way.
May I just make a comment? Hello, Liam.
Yeah.
So regarding the question of if there's some prescribed, some preferred Calabi-Yau, so just I wanted to make a comment. At least from H1 equal to 2 analysis of all these CCs and clusters karke, we found that K3 fibered Calabi-Yaus preferred more these flat vacua than the other ones. So in that sense, but it is only shown. So it's just like an observation for H1 equal to 2 only.
Yeah.
And it would be very interesting to find for larger H1.
Yeah, that's
Whether
right.
these K3s fibered are really singled out. Okay, thank you.
Yeah, no, absolutely. So right, there are some variations in prevalence, but the prevalence overall, I think, is quite high. And as you'll see later, the way that we carried out this work is by building hundreds of millions of these vectors. I'll explain by the end why we needed to make this so. Okay, so I described the racetrack mechanism, and the point is, the reason I wanted to talk about that is we can select PFEs that yield racetracks. Remember, the PFE so far was some sum of GV invariance times polylogs, but that's secretly a sum. That's just a sum of exponentials, and it's in principle an infinite sum, but with known coefficients and known exponents. And what we can do is we can select cases where it so happens that two terms compete and the subsequent terms are subleading. And this is not an uncontrolled approximation. This plus negligible, I can compute as far as you want along there and show that they're negligible. So this is not like the unknown quantum corrections we were talking about earlier in the talk. These are very much known. I'm just not going to write them. And so we just post-select cases that give a racetrack. Here, these prefactors are some integers that you can compute. They involve the fluxes and the geometry. And the exponents involve also the fluxes. Okay, so it's all integers at baseline. And since everything's purely exponential, the vacuum energy is naturally exponentially small. That's pretty good. So now let me fulfill Shiraz's wish from a few days ago to come up with something that's concrete and finite. So here's a concrete, finite flux superpotential. Here's an example with 5 complex structure moduli, 113 Kähler moduli. We find quantized fluxes given by these vectors of integers such that there's a direction in the moduli space along which the polynomial part of the superpotential exactly. And so I told you before there was going to be a flat direction, one flat direction. This part is potentially confusing. That flat direction involves relating the complex structure moduli, of which there are 5, and the axiodilic. They're related by some purely constant rational vector. So there's a H21 plus 1 dimensional moduli space, and in that moduli space there's a ray, and that ray can be parameterized if I want by the axiodilic. I will do that. Okay? And along this, the polynomial part vanishes exactly. What remain are world-sheet instantons on the mirror, and the leading ones have GV invariance -2 and 252. And so then the superpotential looks like, you can check this. The thing in red is the stuff that I'm going to care about, and the thing in black is the first subleading piece. But it's a higher power of e to the -1 over g string. Remember, tau has 1 over g string in it. And so I can totally ignore that piece. And then this plus ... again, I can give you as many of these as you want, and they're all small. So what we did, the work consisted of finding a case where these are 729ths and 728ths, and where the prefactors are a little bit hierarchical and have opposites. Well, we just selected a case with that property. So none of this is made up, it's just, we found it. And if you take that superpotential, the moduli are stabilized at g string 0.01, and W's VEV is 10 to the -62. It's sort of understandable when you minimize such a superpotential. The VEV that you get is the ratio of the prefactors to a power that's given by an appropriate scale difference of the exponents. So 2 over 252 to the 29 is 10. Okay. So that's an example of a small superpotential, and that ends the part wherein I describe the mechanism for small w. Now let's see, how can we actually break SUSY? Yeah. Okay. Yes. Yeah, good. When we started, it seemed pretty hard, but we're actually very good at it now. And so, if we go looking on a laptop in some new geometry, with the present version of the code, and you want to find something where W is 10 to the minus 500, we can do that. And we can do that in, half-hour search. We might find, you'll find tens of thousands of vacua, and some of them might have 10 to the minus 500 or some stupidly small. So, yeah, surprisingly enough, this is not the hard part of the computation. The hard part, there's two hard parts. One is building the technology to be able to do the computations at all. Once we did that, getting these small W naughts is not even hard. This is great. The hard part is coming with Susie break. Does that address? Yeah. Yeah, so these exponents here involve the fluxes also. Yeah. So you end up picking the fluxes such that the fluxes just balance out. That's right. Yeah. So these are not baked in. There's a purely geometric picture, but not. Yeah, absolutely. It's coming from twice 29. So basically, the coefficients that show up here, the exponent that shows up here, and these denominators are all variables. So secretly, up to some appropriate scaling, entries of this complex vector, this rational vector, are the things that show up. How did we find one that's 28? Or no, this doesn't have a 28. So this is the reason I didn't write it. It is, of course, 1/. I wrote it as 7/28 so that it's obvious that it's close to 7/29. Maybe it's obvious anyway, but I like that point. Yeah. And what these exponents actually are is 2 pi I tau times this vector dot the vector of charges of the curves in question. And so one of the curves dots with P to pick out exactly one of these components. But then other ones get one. And in principle, there's an infinite sum because we have, I'm supposed to sum over the entire Mori. These are just the leading ones. Yes.
The size of the internal modulus that also fixed.
Perfect. That's where we go now. So, thanks. So we talked about these moduli, and so far we've been playing a game with the flux superpotential that involves the axiodilaton on the complex structure. But how about the kilomoduli? So in general, there's a superpotential that involves all of the moduli, the non-perturbative superpotential. Why not? And so far we just worked with the flux part. Now we've got to compute the non-perturbative superpotential and see what happens to the. I'm going to flash some formulas here in case there are some people who want to see the detailed form. But this is perhaps not a key part of the story to go through the details, so I'll be brief, and it won't hopefully corrupt your understanding of the remainder. So the general form of the non-perturbative superpotential is the sum over Euclidean D3 branes wrapping divisors. This D means a divisor in the threefold, so 4 cycles. And there's some Foppian prefactors, one with determinants, and an exponential of the complexified volume divided by a dual Coxeter number if there's a gauge group on 7 branes. That's the general form. And we find cases in which it's a little bit simpler. It's not a sum over all divisors, but it's a sum over prime toric divisors. These are special ones determined by 0 to 4 coordinates, plus some negligible stuff. And so that means that instead of an infinite sum, we have a finite sum plus an infinite additional sum that we know is something. That's the work that we do. I'll bury that. And we pick cases where the Foppians are constants. Now, by pick cases, what I mean is there's a topological condition that ensures this. If you're a fan of such things, I can tell you afterward. We can't compute these Foppian numbers, but Ashok and others are engaged in work that will, that has laid the foundation for computing them. And perhaps you're on the cusp of doing it. I don't know. But what we do in the remainder of the analysis is we come up with an appropriate representation of the Foppians in terms of integers for a duality. And then we sample a huge range, 7 orders of magnitude of values of these things, and we find that doesn't change the vacuum structure. So I don't really care exactly what value. I mean, naively, they should be order 1, and as long as they're not way outside this range. The volumes, that's coming. Yeah. Yes, please. Pardon me? Those are integers, correct. This is not actually integer, yeah. So, sorry, thank you. What I think, indeed, this is a fictitious range if you believe this quantization argument. Good catch. We studied it because this is not a theorem that it's quantized like this. And so for avoidance of doubt, we studied this fictitious range and it didn't matter. But really, I think this number should be 1 or 2 or 3, etc. Yeah. Yeah, very good. Yeah. Yeah. There's a fermion zero mode counting that we do, and we do it all explicitly. We don't say, oh, hopefully this has an instanton. We check that the number of fermion zero modes is 2 and not more than 2. And so there's a superpotential term. And we can compute the semi-classical action because we know the volume. Okay? And so now, where do these things get stabilized, right? The question is, where in Kähler moduli space do we end up? And to address that, so, please. Yeah, so it's schematically, it's that these can be dualized to a case where you're seeing these terms, seeing similar instantons with GB through factors. So you can get the quantization from That's an excellent point. I can't currently. We haven't tried very hard. I should say the conceivably more interesting duality that was mentioned here is a duality of all of these configurations to M3 on an empty G2 manifold. By empty, I just mean not a flux compactification, just a G2 manifold, where these are Euclidean M2 contributions. And that's another version of an answer to your question. So what Moritz also did was look at Euclidean M2s and argue for quantization of 3 factors. I suspect that that's the statement, but I don't want to be too precise about it. We can look, but I think that that's the statement, yes. Right. Happily, very little hinges on the exact values of these, but now so now here's the complete summary of everything we've done in the supersymmetric case. I told you about each of these parts. What are the moduli? The superpotential is the sum. We manipulated choice of fluxes to make the flux superpotential be a sum of exponentials, and then we computed that the non-perturbative superpotential is the sum of exponentials. So we've got 2 different kinds of exponentials, but that's it. And now we want to solve the F-flatness conditions to find a supersymmetric vacuum. That's the next step. Okay? And n equals 1, ADS4 vacuum. So here's the space in which we're working. This is a cross-section of the Kähler moduli space, or Kähler cone. Each little polygon here is a different chamber. To go from one chamber to another one of a different color, you're going through a flux. So there's an awful lot of chambers to navigate through. And the situation you might end up in is where you sort of start your search here and you want to find an F-flat point. And we figured out a way to sort of navigate through all of these things, plot your way through to a supersymmetric vacuum. So that is a solvable problem. And it'll come back, actually. So we find a supersymmetric vacuum. And having found a SUSY vacuum, that's a vacuum of the leading order theory, like the theory I already told you. And Shiraz, I can now answer your question. How big is it? Because you're comparing exponentials in the 4-cycle volumes to a flux superpotential that's a small constant, the 4-cycle volumes are log of 1 over W naught. Since W naught was 10 to the minus 62, this is a relatively public size. So that's how big. Now, however, there's 2 kinds of sizes we should think about: 4 cycles and curves. And it turns out not all the curves are that big. And so that's why, having found a point that gives a vacuum of the leading order theory, I better check that alpha prime corrections are under control. And the leading ones, this is a relatively long story, but the leading ones turn out to be world sheet instanton corrections to the Kähler potential and Kähler coordinates. Okay, there aren't world sheet instanton corrections to the superpotential, because those wouldn't be. But there are world sheet instanton corrections to the superpotential. Well, we can compute them explicitly, because we can work out the mirror map even in hundreds of dimensions. And so, yes, please. Yeah, there are perturbative alpha prime corrections, and I'm very worried about them. Well, okay, I'm not that worried about them. The dominant effect parametrically dominant affecting regime where we're working are these. But that doesn't mean that the one string loop corrections to the Kähler potential are formally utterly negligible, but they do go like G string, and G string is kind of the minus 2. So they are suppressed. These turn out to be almost order 1 effects in some cases, and there's a G string saving us. So that's the reason that we can afford to.
So I just want this alpha peptides is not.
Ah, yeah, very, very good, very good. So before you go to the string loop level, if you're just working at the level of the classical theory, you're just seeing the n equals 2 data. And the n equals 2 data truncates at only the Becker-Hach-Lewis alpha prime cube term. We include that, but there's no other perturbative series. Down by 1 G string, exactly. So we're living secretly off of breaking n equals 2 to n equals 1, not that bad, but by a factor of G string with G string. Okay, so I think it's actually sort of a fun story to compute these. I'll just show you 2 slides on it. We want to find the radius of convergence in the Kähler moduli space. Okay, so we want to know, so T is a vector of 2 cycle volume. We want to know what's the T min. This is an H1 one-dimensional vector of 2 cycle volume. We want to know what's the T min such that as long as my T vector's length is bigger than the length of T min, further out in the Kähler zone, then the following sum decays exponentially. So what's the sum? This is a sum over world sheet instanton wrapping a curve, a degree 2 world sheet instanton in the same class, degree 3, etc. Just multiply wrapping more higher and higher multiples of some basic curve. And if this quantity decays exponentially with n with the degree, then the world sheet instanton series is under control. Now, if we were working with a model with 2 or 3 Kähler moduli, we could analytically figure out the radius of convergence. But here we can't. The example I've shown you is 113, and that's just completely out right now. But we can compute GB invariance to a very high degree. So in that example, I pick some curve, I'll repeat it for other curves. Pick some curve and just compute the GB invariance C of 2C, blah, blah, blah. Up to. But then let's keep going. We'll compute the GB of 100 times C. And we'll get some result. And the point is that if you check on a log plot, this is an exponential increase with an extremely stable rate. Whereas this is also an exponential with a fixed rate. And so we can just ask which rate is bigger. Now we can choose T to be big enough to beat the growth of the GV prefactor. Okay? So this is how we're going to do that. And now I'm going to plot here. For a bunch of different curves, I'll plot the quantity that we want to not grow as n increases. Here's n, the degree, and here's the log of the quantity in question. And what we see is this. So each stripe is a different curve class, and along it we compute the GVs to a relatively high degree, and you see that very cleanly they decrease in importance at higher degree, so everything's under. Okay. So that's an example of the kinds of cross-checks one can do in this setting. So now, in the last few minutes, let me turn to de Sitter vacua. How do we break supersymmetry? So Sandeep made 2 claims in the famous 2003 paper. First claim, in type 2b compactifications with small superpotential, there can exist well-controlled supersymmetric vacuum. Second claim, you've got such a vacuum, and it has more things. It has Lebanov-Strassler probe with 1 or more anti-free branes. But as those things as well, then there can exist a metastable supersymmetry. Not there always exists, but there can exist. Okay. Those are the pieces we need. And there's been, of course, intense scrutiny of this idea. And the basic question we want to address is, do there exist consistent realizations of this? So what are the requirements? Small superpotential, like Lebanov-Strassler probe. And the first 50 minutes of the talk, I've explained the first part. We've done that. Now, let me briefly sketch how we do the remainder with the same tools. We won't have to go into as much detail. Fluxes cause warping. So you want to warp conifold, you just have to choose the right fluxes. And this is, I've written here the warp factor in the Klebanov-Strassler solution in terms of the flux quanta, K and M. And we can adapt, I won't bore you with showing how to do it, we can adapt the Diophantine problem that we faced before to give not just a small superpotential, but a small superpotential that stabilizes the complex structure moduli near it. The Klebanov-Strassler solution is a warped, deformed conical. So you take a Calabi-Yau that's near a conical point of its moduli space and put in appropriate fluxes, a KS throat pops out. So we can manufacture compactifications with K. Now, controlled supersymmetry breakage from an antibrain requires not just that there's a Klebanov-Strassler throat, but that it should be weakly curved. So that means that the flux around the free sphere at the bottom of the throat is times d string needs to be a large. And we need the antibrain configuration to be metastable, right? It's all fine to chuck in antibrains and break supersymmetry. We want to metastably break supersymmetry, not just create some runaway. And that in particular requires, as Katri Pearson and Verlinde showed, that m is bigger than 12. It's not the integer 12. Although 12 suffices, there's a more detailed calculation. And finally, all of this should be consistent with Gauss's law. So we want to put in an antibrain. There has to be enough space in the D3 brain tadpole for that to be a consistent configuration. Because it's compact, so the total charge has to be 0. So the total charge of the fluxes plus the O-planes plus the number of D3 brains minus the number of antibrains has to be 0. And we're just going to choose compactifications where we can put in one antibrain, where we're in fact compelled to put in one antibrain. So we do that. And so now we've achieved all of these requirements. And so all of the basic pieces needed to assemble a KKLT vacuum have been achieved. And all we have to do is assemble and test. This. Yeah. Very good. Very good. Yeah. We have to use a fake configuration where, so here, if I don't put an antibrain, I violate the tadpole. Nevertheless, it's a mathematical object that I can study. It's not a physical solution at all. But then once you add the antibrain, it is a physical solution. So we call them precursors because they really are just, they're sort of bookkeeping devices to help you find a physical solution. Yeah, very exactly. So we ignore the tadpole, compute the superpotential and the Galois potential, put in the antibrain, and then to ask how does the antibrain affect those data, we back react it using 10D supergravity. So you have the antibrain at the bottom of the throat, you find the Green's function, you know how it's affected. Yeah, thank you. M is. So Mi with range H1 is a vector of flux integers on A cycles. And this is a vector of flux integers on B cycles. And sorry, I should have said, there's one preferred 3 cycle of the Klebanov-Strassler throat, the 3 sphere at the tip. And M with no index is the flux on that side. Another way of putting it is it's the number of D5 brains that you have to dissolve to make the Klebanov-Strassler. That at least 12, yeah, bigger than 12 in fact. At least 14, it ends up being even. Oh, yes.
Yeah, but of course it gets
Yes.
clear, but
Yes, that's certainly true too. Yes, and there are reasons we might play those games, but not yet. Great. Okay, so now in case some of you are lost in the sort of complex strategy, I'd like to bring this back to what the key physics mechanism is that's going on here. We're living off of 3 exponentials. Okay, and that's perhaps the thing to take away. We develop computational geometry tools to deal with flux compactifications so that we could make 3 exponentials compete. And here they are. One of the exponentials is the flux superposition that we dealt with. We had a sum of exponentials in the channel, and we use that to make the flux superpotential relatively small. Another one is the sum of instantons from Euclidean D3 brains wrapped in 4 cycles. Those are exponentials in Taylor model. And when we put these things together, we found a supersymmetric. And the last exponential is exponential warping, where the inputs are flux quanta, so integer inputs, and you get exponentially on the scale. So this is a sort of dimensional transmutation type phenomenon, but it's another exponential. And when all of these things play together nicely, you find a de Sitter vacuum. Now, de Sitter vacuum are possible if all of them are commensurate. And 2 being commensurate with 1 happens automatically, because if you dial in a classical flux superpotential, The killer moduli will move around until they find a place where this sum is comparable to that. That's a dynamical process. Those things being equal to the dynamically generated scale of Klebanov-Strasberg probe is not a dynamical process. And so this is the fundamental reason that something hard remains in this work. Like, you might say, why don't we just like quote examples and just make tons of great vacua and be done with it? Why not? Why are we, whining so much? Learning how to compute these various things was ultimately not that bad, and we're relatively good at it now, even in the high-dimensional moduli spaces. The thing that is still brutal is we have to make a huge number of vacua that have all of these things and post-select the ones where 1, 2 are commensurate with 3. There's just two very different scales on a log scale, and you have to draw until they match. So that's why we studied 240 million vacua, of which 33,000 have an antebrain in the throat, and many fewer than that, as I shall tell you, have it. So this wasn't quite hard. So now, actually, this, please. Exactly. Twice the tension of the anti-D2 brain times the work factor of the tip. So that's the energy there. Or much smaller. It's going to be some exponential in the flux fauna, and you can make a vacuum where it's any exponential that you want, but we have still not been able to think of a way to make it be an exponential that's comparable to this one automatically. You'd have non-SUSY ADS, exactly. That's interesting too, but one wants to say. It's an instant runaway. It has to be within a range of a factor of about 3 of the W constants. So you have a very tiny range, and everything's on a huge log scale. So so that was the challenge. Let me yes, please. Yeah, thank you. Exactly, because the diaphanty problem. My schemes have gotten better. Now we can do much more, but in 2024 we can only do up to 8, because that ends up being a twice H21 plus 2 dimensional lattice, and it's still a slightly annoying problem. Yeah, exactly. Yes. Yeah, very good, very good. That's the key thing. And in a sense, this is another one of the key insights of the KKLP paper, which is that antebrains break SUSY at the string scale over G string. And only if you can somehow suppress that breaking by a great amount can you possibly make sense of a metastable configuration. And what's happening here is just that there's an exponential suppression, because the breaking is happening in the IR of a throat, and you propagate any sorts of supersymmetry breaking effects up via the Bulk-Green's function, and they're exponential. That's really, you can do that calculation directly in supergraph. You think of it as an RS model with SUSY breaking on the IR brain, and on the UV brain you see a very feeble effect. Okay, so let me skip over the mechanics of the search. Yes, please. Yeah, we chose conifolds because a Klebanov-Strasberg probe is a warp-deformed conifold. So if I end up near a conifold point in moduli space with a suitable number M of fluxes through the A cycle, and a suitable number through the dual B cycle, then a KS throat results. A finite KS throat. That's why we did that. Okay, so we search in the same space, and where we found a de Sitter vacuum nearby, where we found SUSY vacuum nearby, we find a de Sitter vacuum. We find 30. After all of this work, and that is the upshot of this fine-tuning 3 exponentials to meet each other. We can do better now, but we still have not cracked this to make this an easy problem. Okay, so let me close. Yeah, let me show you the example. So here's the sort of key example. Claviatoric hypersurface with H218 and H150. You pick these fluxes, and there's a KS throat with 1 antebrain. And when you include the antebrain potential computer, I stress that leading order is deep screen and out, which is the same approximation made in we find it at this level of de Sitter vacuums. This is the main finding. The main claim, we find the EFT in the way that I've described it so far has de Sitter. And to the extent that these corrections are small, they could be de Sitter vacuum of the full string theory, but we do not make that claim. And here are the data. Actually, let me show you the data. Here, I'll show you the data all together, and we'll talk about the parameters. So G string is 0.06. That's very healthy. W naught is not that small, but it turns out to be. We can do the analysis carefully. The cosmological constant is 10 to the minus 19. This is the mass dimension 4 quantity, but that's still plenty. Yeah, of course, we're never going to solve the cosmological constant problem in an interesting way in these models because we haven't included like electroweak symmetry breaking and who knows what. So I make no claim whatsoever about that. But in terms of the hierarchy of scales between Planck scale and our energies, yeah, it's comfortable. That's in the, yes, very good. That's in the supersymmetric vacuum. So we do find supersymmetric vacua that have vacuum energy 10 to the minus 122. And in the de Sitter ones, the best we've done is 10. But with this plus, we pay dearly for that plus. Now, but the thing I should close with before going to my concluding slide is G string M here is 1.05, and that's just not big. And so the analysis of metastability is not naively applicable. And so we're going to have to wait and see what alpha prime corrections to the anti-brain action do in this setting. So if we made an error budget, since we can explicitly compute the superpotential, all we're dealing with there is truncation. Sorry, it's a little bit small. The corrections to the Taylor potential in the alpha prime expansion are also extremely small. G string corrections are order G string, and then corrections from the anti-brain potential are possibly order 1. M here is the integral of F3 over the 3-sphere in KS. In other words, if you make Klebanov-Strassler by taking a collection of D5 branes and D3 branes, M is the number of D5 branes. Very, very good, because the radius of the throat, the radius of the tip of the throat is root G string M in string units. And so when G string M is 1, the sphere at the tip of the throat is order 1 in string units. Now, it's not catastrophic, but it's not safe either. It's sort of on the boundary. So let me try and wrap up the future prospects. Well, we chose this in a place where the search space is big. So there's a lot of vacua we can look for, and we're getting much better at finding things with better control parameters, but I don't have any that are totally tested to report to you now. And in parallel, one would very much like to understand the theory better, right? If we can understand G string and alpha prime corrections to the Taylor potential, as you're asking, compute the Faustian prefactors, compute alpha prime corrections to the anti-prime. And so a lot of work in progress on this. So to conclude, so what did? We took type 2B on Calabi-Yau threefolds. We computed the potential from fluxes and Euclidean branes. We solved the Diophantine problem in the fluxes to produce a 1D EFT, made a 4-dimensional EFT with a 1 model. And we selected cases where competing exponentials gave a vacuum. And in this way, we constructed candidate de Sitter vacuum. We are aiming to compute alpha prime and G string and warping corrections and search for vacua that survive in the full theory. And I think there are bright prospects, aside even from KKLT, for systematic construction of de Sitter vacua in Calabi-Yau applications. Thank you.
Thanks for a heroic effort and an amazing talk, Liam. I wanted to ask you about the alpha prime corrections because G string M is not coming out to be very big. Your worry, just to understand it, is you have this anti-brain now in a curved background sitting, and there's ambient flux, which is sort of supersymmetrically opposed to the anti-brain. So the instabilities could make it dissolve and go away. That's the main.
Yeah, exactly. The anti-brain, it's actually easier to describe if there were more anti-brains. So because we have a small number of anti-brains at the tip, the Myers effect causes them to puff up into a 2-sphere inside the 3-sphere. And that's, in principle, unstable under the 2-sphere expanding, rising past the equator, contracting on the far side. And at that point, the brains have annihilated its flux, which is the process we described. And the worry is that Gottfried Pearson Berlinde calculated the conditions under which the thing is metastable, it can't get all the way to the equator before being stopped energetically, and it lives long. And the worry is that that metastability criterion is changed by, for example, Riemann squared corrections. And some of those have been computed, but not all corrections at that order have been computed, and that's why it's up in the air.
Okay. And then just a quick follow-up, if I may, which is, I mean, of course, this was heroic, and you found that the G string M in all the cases was not very big. But do you see a kind of in principle reason to be worried, or is it just that this large search still yielded only?
No, it's honestly, the reason that G string M is small is that G string is so ridiculously small. It didn't need to be 10 to the minus 2. I would have been happy saying that the string coupling expansion is well controlled if G string were a quarter. And the thing is, the mechanism that we work with happens to spit out very small G string. We have a different mechanism that we're currently working up that gives similar kinds of vacua, but with bigger G string, like a quarter or a half or thereabouts, and then that will change this by factor. If you want a G string M of 60 or something, I don't think I could ever do it. There's nothing that exists in this kind of landscape. But if you want G string M of 5 or 10, I think I could do it.
You can't make M big?
Oh, I can make M as big as you want, but then you need to also match all those scales. The 3 exponentials don't compare once M is big. Yeah, I can find examples with M of like 108 or something, but then the things don't all line up.
Totally fantastic talk. Okay, one quick question. Suppose you were doing particle physics in this background. What scale would you see supersymmetry breaking? Where would you see them?
Right. So the moduli mass, because of the coincidence of these 3 exponentials, the Hubble scale associated to this is also the scale of the gravitino mass and the scale of the mass splittings in supermultiplets that are coupled gravitationally.
So you would just see a supersymmetric universe to very high accuracy if you were an observer in this universe.
If you were an observer in this particular universe, no, I mean, this would certainly look like the sitter. The problem, I would say, is that the moduli mass scales and the gravitino mass are comparable.
No, sorry, if you were just doing particle physics, you were doing LHC in this universe, you would see particles appearing more or less in supersymmetric multiplets?
Well, it depends on how accurately you were doing things. I mean, this is V, so Hubble is square root of this, so it's 10 to the minus 9 in Planck units. So the mass splittings in supermultiplets, the associated gravitino mass scale is like the intermediate scale. So 10 to the 11 GeV or something like that, if I did it right on the fly, or something like that. So it's relatively high scale supersymmetry breaking here.
Relatively high speed. So help me understand the following thing. I mean, it's probably a very stupid question. Suppose I was just doing a loop, and I computed the contribution to the cosmological constant from a loop of some matter field.
Yeah.
So then that would give you a cosmological constant up to the supersymmetry breaking scale.
Yes.
And that would be of this order?
Yes.
Okay, thanks.
Exactly. And as related to the previous question, the reason that this order is not the cutoff scale, is not the ultimate cutoff scale like the Kaluza-Klein scale, is because of warp. So everything gets cut off at the warped the warped energy scale of the IR, but they do run up to that scale.
Maybe just the last question.
I wanted to ask, so you are saying that you can increase G string a bit. So, but when we increase G string a bit, then the whole series of string loop corrections will kick in.
Yeah.
So that is one just a comment. So how many scalar moduli you fix actually? So it looks like, for last more than a decade, we have been busy with fixing scalar moduli, taking the GKP. Now you have switched the table in the sense that now we can easily stabilize complex structure moduli, but the H11 is very large, right? Yeah. So do you think that by the time you try to kind of manage all these H11 minimization, the scalar moduli stabilization, the problem will somehow reappear? Or I mean, what is your plan for having the scalar moduli stabilization? So you stabilize all the 115?
Everyone. So I skimmed over that part. So when I say this potential, for obvious graphical purposes, I only show the overall volume. But what I was trying to sketch was that we pick a point in the actual 150-dimensional space where we can check the Hessian is positive. We do literally the whole thing.
And what is the wave in that case? I mean, how much volume they receive?
Log W naught. 2 pi t is like log
each
W.
of them. Okay.
Yeah.
Okay. Thanks a lot.
So if that all works, So
Yeah, we can probably.
the EFT, the question is about corrections of the EFT, but within the EFT we stabilize.
Okay, thanks. Sir.
Thanks, Liam.
Okay. Yeah. Can you hear me? Is this working?
Okay, so
Okay.
next we have Sunil telling us about contour integrals for 4D superconformal field theories and 2D about national CFTs.
Thank you. Thank you. So I'd like to start by thanking the organizers for last night's wonderful dinner and also for organizing this wonderful set of lectures. And let me start. So I'll be talking about this paper that came out last week with Ramesh, who's in the audience and who will speak after me, also on the same paper. So when I was younger, I used to get very annoyed when in conferences two collaborators would rig it so that they can have successive talks on the same paper. It seemed like stealing somehow the time. And so, but as I get older, my ethics is weakening a bit, and I guess now that I'm doing it. Anyway, I'll also, so the bulk of my talk actually will be about this paper, which is 36 years old, and my collaborators are in this room, and also this paper, which is more recent. So about that 36-year-old paper, this is its citation history, which looks not so bad till you realize that the scale is 1 unit. So this has 7 citations in 36 years. All of which are by the same authors, except one, and that exception is Devashish actually and Arjun. Anyway, so it's not in any top million list, but it suddenly turned out to be interesting for a problem, and I'll try to explain that. So rational CFT are those 2D CFTs for which there's a finite number of primaries under some chiral algebra, which is typically an extended one. They have rational central charge and conformal dimensions. The chiral algebra is known as a vertex operator algebra in mathematics. It's a rich subject in mathematics. And these VOAs or rational CFTs appear in many different contexts in physics, from critical phenomena to string theory, Chern-Simons theory, fractional Hall effect, topological phases, anyons, all kinds of things. Now, one of the unusual places where these VOAs, vertex operator algebras, emerged is in the context of 4-dimensional superconformal field theories with n equals 2 or greater. And this this subject has an older history, and Abhijit is actually one of the leading experts in this, so he'll be glad to answer any questions, which I can't because it's a new subject for me. And so this is like some kind of last stage development, or one of the more recent developments in a series of attempts to understand some kind of 2-dimensional vertex operator structure sitting inside 4D superconformal field theories. Importantly, the 2D CFT or vertex operator algebra need not be supersymmetric, even if the 4D theory has to be. Okay, so I'll call this the Schur VOA correspondence because it involves some special operators called Schur operators. And I'll be talking about this correspondence. Now, what is it? Well, there's the famous superconformal index, which depends on 3 parameters, Q, P, and T. I'll define it soon, and also some flavor fugacities. And there's a specialization of it, which is called the Schur index. And this quantity is just a function of just one parameter Q, and it has a Q series which looks very much like a modular form. So powers of Q with integral coefficients. And it turns out, so one of the key results particularly of this paper is that this Schur index, which is an interesting quantity in the 4D theory, matches the characters of a 2-dimensional rational CFT. And it's this that we'll be talking about. So both sides share modular behavior under SL2Z or a subgroup. In the case of rational CFT, that has to be because of these are defined because their partition function is a path integral on a torus. In the case of the Schur index, as far as I understand, it's not at all obvious that it has to be. There have been works arguing that it should be modular, but it seems a little bit surprising at first sight. Also in RCFT, you get characters, many of them, different modules under the algebra, but in the Schur index, you basically get one quantity, one function of q, ig of q, and that matches one of the characters of this rational CFT. Okay, so the precursors, well, there's old work from 2 decades ago, Gukov-Witten, where they talked about 2D surface defects and found chiral algebras. There's the AGT correspondence, which relates 4D instant-on partition functions to 2D conformal blocks. And then there's the seminal work of Abhijit and collaborators on Schur operators, and showing that they have in particular closed algebra, and they related them to 2D, if I understand, to 2D Q deformed angles. I won't be using anything of these works other than what's in the later works, but I'm sure they were inspired by these. Okay. Now, so in many cases, this correspondence has been found that you have a 4D superconformal theory. Now, from now on, I'll be in n equals 2, not n greater than 2, supersymmetry. And you start with a specific 4D theory. You find its Schur operators. You calculate their operator product. Okay, so these are operators localized on a plane, or you can think of them as surface operators. And then you find compute the OPE, and you find that it has a Virasoro-like form with the some multiple of this 4D central charge appearing in the leading term. Then you can identify that with the Virasoro algebra if the 2D theory has a central charge related to this 4D by some relation. Ramesh will talk in more detail about the actual relations. And then that gives you the idea that there's a vertex operator structure, and then you know what you should look for to match the Schur index with a 2D character. So ultimately, this leads to an identification that the Schur index, which is this quantity, and I'll define it in a moment, is some character of a 2D CFT. And this is in some sense case by case. So you pick some 4D theory, and then you calculate this, and then you find out what's the 2D vertex algebra, and then you calculate that, and then you realize that they are in fact the same. Okay. One important fact is that the 4D 2D relation between central charges has a minus sign. So assuming the 4D theory is unitary, then the 2D theory cannot be. Okay. But this is only true in this specific, this Schur VOA correspondence, and there's something more general, which I'll talk about, and Ramesh also, where you'll actually find relations between 4D and 2D, both unitary theories. So, okay, and examples of this will come in the next talk. So now let me talk about this new development from this year. Deb and Rajamat a few months ago, I think in June this year, defined a generalization of the Schur index, which they call the Schur partition function. And it has the property that it's a Q series, but actually depends also on a parameter alpha. So it's a specialization of the full superconformal index of P, Q, and T. But in the usual specialization, you only are left with Q and you get the Schur index. In this specialization, it's some sort of slightly double, like a double scaling limit, and you're left with 2 parameters out of 3. And it has the property then that if you set this parameter alpha to 1, you go back to the 1 parameter Schur index. So it generalizes that. And what they found was interesting. They found for one thing a 4D relation, which says that the generalized Schur partition function for some particular alpha equals alpha tilde is the Schur index of some other 4D theory. So G1 is the gauge group of one 4D theory, G2 is for a different theory. So the Schur index of this one is the generalized Schur partition of the other one at some value of the parameter alpha. And as you scan over alpha, you apparently reproduce a lot of different Schur indices for different groups G2. There is some physics, seems to be some connection between G1 and G2 from the fact that they lie on the same RG trajectory, but I won't be discussing that in more detail here. I think Ramesh has some comments on it. And okay, so because of this relation and also the fact that the right side, the Schur index, is a character of some CFT, therefore the left side is a character of some CFT. Yes.
This alpha parameter comes about, what exactly?
Yeah, I'm going to do it.
Okay.
Next slide. Okay. So this is actually a very broad overview, which I'll zoom in slightly, and then Ramesh will really show you the kind of nuts and bolts of how it really works. Yeah. So the point I was making is that since the Schur index is known to be a rational CFT character, it means that the generalized Schur partition function for various values of alpha will be a CFT character for various values of alpha. And this is a nice relation because you might be tempted to extend this to sort of all values of alpha. Could it be that there's a family of functions in 4D, the generalized Schur index, which matches a family of some kind of character like of vector valued modular functions in 2D? And that's exactly what we'll try to argue. So to be more concrete, we start with 1/8 BPS operators. This is the relation that the conformal that the scaling dimension satisfies in some choice of units, in some choice of conventions. J2 appears. So then J1, J2 are the angular momenta of S4. This is a theory on S3 cross S1. So its symmetries are isometries are S4. R and R, as usual, are the R symmetry representations, and this is the actual superconformal index, except for a factor involving flavor fugacities, which I won't, which I've just removed. Now the Schur limit is setting q equals t, and what happens when we do that is that these two terms combine, obviously, but also not obvious from this expression, states with J2 minus J1 minus R not equal to 0 actually pair up under supersymmetry and drop out from this. So therefore, effectively J2 minus J1 minus R becomes 0, and therefore the resulting quantity becomes P independent. So we simply set Q equals T and it just becomes P independent, and this is the answer. And so this is the Schur index. Okay. Now the double scale limit instead, which is the one introduced used by Deb and Razamat, but it's actually dates from an older version of this limit by these people, is to write, instead of writing q equals t, you write t equals q times p to the 1 minus alpha, let alpha be a parameter, and then you send p to 1 with alpha fixed. And at the end of doing that, of course, t is equal to q, but actually alpha hasn't disappeared from the problem, and you find some quantity which depends on alpha, and that's the generalized Schur partition function. So under that, this function, the full index goes to the generalized Schur. Yeah. The Schur index counted Schur operators, which are a specialization of, is it 1/4 BPS operators? Is that right?
It's probably resolving.
Yeah, probably true, because they satisfy this to be 1/8 BPS and then also this, which is another pairing under a different supersymmetry. Yeah, so alpha thing, actually it's not clear what it counts. It's really a limit of a calculation rather than a calculation of an index. You have to calculate the index and then take a limit. So yeah, I don't know if that's even clear. It's not at least clear to me what it counts, that it counts something. It's as I said, it's a limit. It's, like sort of in ADS CFT, you have a BMN limit. There's a duality, and then it has a limit. It's not like there's something directly you can count. You can say that it counts that thing. Yeah. No, not necessarily for all alpha. We'll see that in a moment. It's actually exactly, good point, Loga. So for general alpha, it's in fact not integral. It's not an integral, it's not a Q series with integral coefficients, so it really can't even be counting. That's correct. Sporadically, for different values of alpha, it becomes integral and counts this. That's right. Yeah, sorry, Ashok. Yeah. That must be true. And yeah. Yes. High line. Yeah. Yeah. And that's right. And in fact, this quantity diverges, I think, in that limit formally. So one has to do some regularization to define it, and that Deb and Razamat have done. And again, Ramesh will talk about it. just a real parameter, but actually they like, so Deb and Razamat like to take it positive. We'll take it both positive and negative, real or even complex in principle. I mean, originally the parameters t cube, yeah, you could take it complex. I think. Okay. So it's something which generalizes. So, so in this limit, the super conformal index becomes the generalized Schur, and the generalized Schur in turn at alpha equals 1 goes over to the Schur index. This is the structure. So there is some physical motivation here, and but I'll focus on the mathematics right now in order to make the connection with 2D CFT. Okay. Now the nice thing is that they provided an explicit expression for what it is, and so for the experts right away. So this is the generalized Schur index for a general Lagrangian n equals 2 CFT in 4D with some group of rank, gauge group of rank G. And then basically this numerator here is the contribution from vector multiplets, and the denominator is from hypermultiplets, and this delta is the van der Monde. So if alpha is 1, then delta together with this becomes a Haar measure, and this thing becomes a standard integrand for the Schur index. And when alpha is not 1, then this is a quantity which is just, it's the same integral if you like, but with the integrand raised to the power alpha. So that's really what it boils down to. Okay. And we'll see an example in SU2 which is much simpler than this. So now let me talk about the result of our paper. So this paper, as I said, came out last week. This is with Ramesh, who's here, and with Palash, who's a postdoc in Milan. Ramesh is a postdoc in ICTS. And the main theorem is that, claim is that each of this generalized Schur partition function as a function of alpha solves a modular linear differential equation whose parameters are determined by alpha. And a lot of things follow from this, because the modular linear differential equation for arbitrary alpha does not really give you any kind of integral form, but for specific values of alpha, by some miracle, it gives you different CFTs. And this is sort of seems to explain why this Schur, generalized Schur has nice properties at specific alphas, but it does more than that. It gives us parametric correspondence between some 4D and some 2D quantity. And yes, sorry. Here. Other in the sense? No, this is Z at alpha. So so alpha will determine the coefficient of the MLDE. Okay. Or if by other do you mean the different characters? Yeah. The different characters. Yes, one of them, exactly. One of them. Now it turns out that actually in the 2-character case, which is the rank 1 case in 4D, then alpha going to minus alpha just gives you the 2 characters. For the more general case, I'm not completely sure what the statement is. Yeah. Okay. Yeah, I'll show you that in a moment. Yeah. So this creates a parametric relation where both sides are functions of alpha and solve the same differential equation, and I'll show you that in an example. And the proof of this proposition in blue, we have proved this only for one infinite subfamily, really speaking, the USP 2n 4D theories, which include SU2 with NF equals 4 as their lowest term. For others, the work is still ongoing, but for this we have a very precise proof, and it relies on this old paper about contour integrals, and I'll turn to that and then I'll stop. Doga, how am I doing with time? 10 minutes, this should be good. Okay. So this is the definition of RCFT characters, and this I think people have seen many times, is the standard expression for a modular differential equation on the torus moduli space, with D being some Q D by dQ plus some E2 Eisenstein, which makes this a covariant derivative, so that when it acts on modular forms, it returns modular forms of 2 units, weight 2 higher. And there's a finite basis of modular forms for any weight, but in fact here these can be meromorphic. This is a well-known phenomenon which is related to this so-called non-vanishing Wronskian index. And so there can be more than you imagine phi 2k phis for any given value of 2k, the weight, and the number of different, so the different phis are labeled by the index I. It just tells you how many different forms there are. Each one has its own coefficient, and then these mu's are the parameters, in the free parameters in the equation. And this equation can always be solved in a Q series in terms of the parameters mu, Although for certain values of mu, you also get logarithmic solutions, and then it's more complicated. Pretty much known why that happens. Okay. So the coefficient functions phi 2k, these have in general poles in moduli space, though the characters themselves do not have. The characters are holomorphic except at infinity. And if the phi 2k's have poles, then we count the number of poles as L by 6, and then L is called the Wronskian index. And it will turn out, for what we are going to discuss today, L is 0. So just telling you this because it provides a constraint. So if you parameterize the solutions of an MLDE by these leading behaviors for an obvious reason, then it turns out that the sum of all these exponents plus this, which is the order of the MLDE, is the value of L. So if L is 0, then for any given MLDE, this is a linear one linear condition on the central charge and conformal dimensions, leaving n minus 1 of them independent. Okay. Okay. Now a series. So the reason why we wrote this paper 36 years ago is that just solving an MLDE by the Frobenius method gives you a Q series, but a Q series is not much use by itself to find the modular transformations of the object, which are in sort of highly non-perturbative in Q. We need a functional representation. For low enough order MLDE, it's enough to use, you can just use hypergeometric functions. But we wanted to see if even for MLDEs of high or arbitrary order, we could find some explicit functions that solved it. And what we did was to map the Q parameter, which in turn is e to the 2 pi I tau, via this map into the lambda function. And this is a more useful, so this function turns out useful. It used to be called the Picard lambda function. I think now it's just called the lambda function, modular lambda function. The nice thing is that under modular transformations, lambda just goes to 1 minus lambda under the S transformation and to this under the T transformation. So lambda, so this is easy to check. If you have a function of lambda, it's pretty easy to establish what it does under lambda going to 1 minus lambda. It's much simpler than tau going to minus 1 over tau. So here are the actual contour integrals that were the subject. So we stole them from Dotsenko and Fatehev's paper, which is famously about 4-point correlation functions in minimal models. The point is that there's one cross ratio there, and you can just use the same mathematics, and instead of that cross ratio, you have the complex parameter lambda, which is just another variable in place of q or tau. And we said, okay, so they work for correlators. Do they work to describe characters? And they depend on two parameters, a and b. P itself, p which is outside, is just a function of a and b. Okay. Now, how many of these are there? Well, the integrand is the same for the entire family of JAs. So these are the characters as a runs over 1 to something, I guess n. And what happens is that the contours are chosen, some of them, a of them go from 0 to lambda, and all the rest go from 1 to infinity. Okay. And this you can choose this in all possible ways. We order the integral to be done starting with T1 and ending with Tn minus 1. So you can have no integrals from 0 to lambda or all integrals from 0 to lambda. So there's a total of n minus 1 plus 1 possible choices, and that's n. So those are, the claim is that those will be the n characters. And so you get a rank n vector of functions of lambda. And they all solve a linear differential equation, which is the MLDE translated into lambda variables. And those equations, being Fuchsian, have a monodromy under lambda going to 1 minus lambda, and under that these integrals go into SAB times JB, and this is the modular S matrix. So this solves the problem of finding the S matrix given the characters, so given the solution of an MLDE. If you can make this solve an a general MLDE, and that's the interesting thing. In this more recent paper, where again Palash is a co-author and he's one of the authors of the paper of last week, we provided an algorithm to actually explicitly calculate this S matrix in the most general case. I know you're going to ask, the number of citations of this is 2. Okay. Okay. So we were tempted to associate these contour integrals with RCFT characters, but we realized that they have to jump through a number of hoops in order to actually achieve that. So the first thing you can do is look at those contour integrals, set lambda to its leading value of root q, and then calculate the leading exponent of each of those contour integrals. By the way, this also should tell you that generically the contour integrals will lead to a half integer power q series, not an integral power q series. So even the vanishing of the half integral powers when it happens is a miracle. Anyway, then you can determine C and H of this putative CFT just in terms of two parameters, A and B, on which the contour integrals depend. They are very, very simple linear relations. And the first thing you find is now if you plug the left-hand side into the equation determining the Wronskian index, you find that for any A and B and N, this whole thing adds up to 0. The Wronskian index is 0. So this can only describe RCFTs of Wronskian index 0. So that's hoop number 1. But even with that, we are left with n minus 1 independent exponents, C's and H's. And there's no reason to expect that we can fit this with contour integrals that have only two free parameters, A and B, especially when there can be any number of H's. Well, at least for n equals 2 and 3, it's guaranteed to work, because in n equals 2, the contour integral loses one parameter, has only one, and the MLDE also has only one parameter. And for 3 characters, again, this matches nicely. For 4 and above, it's more complicated. And but what we showed in the old paper was that nevertheless, if you pick many of our favorite CFTs like SU2 at level K, SUN at level 1, and eventually also all C less than 1 minimal models, all of them have the right exponents to be described by these contour integrals. So that's some kind of miracle that we were very struck by, and it's not fully understood even now, I think. But that's not the biggest miracle. The miracle is once you can match the critical exponents of a contour integral with some known characters of a CFT, it doesn't mean that the two functions are the same, because unless you can establish that they solve the same modular differential equation with the same parameters. And the problem is that once you reach rank 6, which is a 6th order modular differential equation, then the equation is no longer determined just by the exponents. It has more independent parameters, and so you are not guaranteed that the contour integrals match the characters. So concretely, for the tricritical Ising model, just matching the exponents with contour integrals doesn't imply that the contour integrals are its characters, but there are tests to see whether the contour integral fit with the known characters of this model, and we carried out those tests. I'll just skip this part very quickly, and found that whatever tests we could do, which involve subleading terms in the Q series, seemed to work. So somehow these contour integrals miraculously like to describe characters of known theories. It's a mathematical result which isn't widely known, as I showed you, but it might be interesting. But here it's very relevant. Okay, so good. So now let's look at the 2-character case, and then I'll conclude. So in the 2-character case, the 4D gauge theory has rank 1. So I should have said the rank of the 4D gauge group is 1 less than the number of characters of the 2D conformal field theory. So that's the relation. And the rank 1 theory is, of course, the very familiar SU2 with NF equals 4. And the Schur index formula that I wrote for you earlier, generalized Schur index, translates into this function. N is a normalization, which is the integral of the van der Monde to the alpha. And then these are some theta functions. U is defined by Z. Z is e to the 2 pi I u, I think. Is that correct? Or I pi u, I think 2 pi I u. Yeah. And so they're simple theta ratio of theta functions, and this is the generalized Schur index in this case. And on the RCFT side, the claim that we want to make is that this solves this MLDE, which is known as the MMS equation, which we found in 1988. Which is the unique 2nd order MLDE with vanishing Wronskian index for some value of mu, which should be determined by alpha, alpha being the parameter in the Schur, generalized Schur. And Ramesh will give you an explicit proof that in fact it does solve this equation, and mu is 1 minus 36 alpha squared over 144. So as I told Ashok a little while back, for alpha and minus alpha, you get the same MLDE, but you get the 2 different solutions of it. Okay. So for every mu for which the MLDE has genuine characters as its solutions, there's a corresponding alpha and therefore a corresponding generalized Schur index. So this sort of systematizes the result. It's a small, I would say, progress towards systematizing the result of Deb and Razamat, which is that this, the result actually of the old Schur VOA correspondence, because we get some continuous families from which we can pick out good solutions, and the generalized Schur is also a continuous family from which you can pick out good quantities at specific alphas. Also for these MLDEs, we sort of know how to pick out the good quantities. So there's been a lot of study of MLDEs in the last few years, and that experience can also probably be used to understand how the Schur in generalized Schur partition function reduces to good Q series for specific values of alpha. So more generally, what we've proved is the same correspondence starting with 4D superconformal field theories with gauge group USP2n and 2n plus 2 flavors. And in this case, it maps onto an MLDE of order n plus 1 that can be precisely determined. So that's an infinite family. There are obviously many other 4D theories, including non-Lagrangian ones for which we even don't know where to start. And there are 4D theories like SU3 with NF equals whatever, 2NC or 6, I guess, where the Q series isn't integral for the generalized Schur. So then it's not even obvious what 2D CFT we should find, but it could be one of these, a CFT under, not modular under SL2Z, but under a subgroup. Okay, so I'm done, and these are my conclusions. So thank you.
If you viewed n equals 4 Yang-Mills as an n equals 2 theory, you can play the same game here.
Yes.
And does the differential equation give you some better way of explicitly finding the index in this limit than computing the integral? Is it easier to solve the differential equation?
The Schur index, you mean, specifically?
Yes.
Good question. I don't know the answer. Actually, we started studying n equals 4 Yang-Mills, but I don't remember even what did we conclude.
For n equals 4 Yang-Mills, at least what we've checked is that they don't satisfy the simple L equals 0 MLDs of the full modular group. So we didn't start working on that yet. But at least for a subclass of n equals 2 theories that Sunil just described, for them, we can make precise statements.
So just more generally, when you have both an integral representation and a differential equation,
yes,
these are different ways of characterizing the same object.
Yes.
Does the differential equation make it easier to solve sometimes?
Yeah, but
find explicit expression.
It does, but one needs to be careful what the differential equation is invariant under. It can be the full modular group or a subgroup of that. I think for some examples like the n equals 4 or even an n equals 2 SUN series, you get a differential equation that's invariant only under a subgroup. So
which is a full modular group, right?
Sunil, there's a question.
Yeah, so the question is, so you found this different Schur characters which are more or less one-to-one correspondence with the, E61, E71, and all the CFTs.
Yeah.
So is there any kind of, or rather any kind of, you want to see these structures in the gauge theory?
Yeah.
Where
I
does
mean,
the G2 come in? Where do they have 4?
Yeah. That's actually, so one aspect of this Deligne series that you're talking about, or Deligne MMS series, already appeared in the work of Rastelli et al., where they found the non-unitary versions of these models. But in Ramesh's talk, even the unitary ones will show. Yeah.
And the second question is, where did that Wronski index vanishing condition, where does it come from?
So in our work, it comes from the fact that this contour integral representation being defined by just two parameters and very tightly constrained, you just sum up the indices and you get 0. So they can only describe characters if the Wronskian index is 0. There might be generalizations of those contour integrals, but we don't know yet.
So I see two things which are kind of opposing each other. One is from all the work we did with theories with Wronskian's vanishing. There are very few safeties which are non-unitary.
Non-unitary,
Yeah.
yes. No, yeah, actually that, let's discuss this. It's too long a discussion.
Thanks. So next speaker we have Ramesh Chandra, and he will continue this talk and generalize 4D partition function and modular differential.
Am I audible?
Yeah.
Yeah. Okay, so let me begin by thanking the organizers. It's been a very fun conference over the last few days. Since Sunil has kindly set the background for me, let me just dive into it. And what I'll be basically doing in the next 25 odd minutes is sort of fill in the details and also give a bit more motivation, maybe wherever I can. And yeah, motivation about why these generalized Schur limit that Sunil defined and which was previously analyzed by like earlier this year and even 10 years ago, why should we care about them, and how modular differential equations might help understanding some of the surprises of this limit. So let me dive right into it. So I'll again go through what the generalized Schur limit is and try to answer some of the questions a bit more and explain why this limit was interesting in the sense of many numerical surprises it holds, and then prove our main result first for the simplest n equals to 2 theory, the SU2 SQCD, and then show that it works for an infinite family of higher ranks, and also probably end with a conjecture about BPS monodromies and MLDs. So that's the rough outline of the talk. So okay, this is already known, and Sunil introduced what the general index is and what the Schur limit is. We just take the fugacities t goes to q, and then it becomes independent of the p parameter. But now let's get to the main issue about taking limits of the superconformal index. One of the main issues is that the order of limit really matters when we take these limits, because we are really probing the area where the full superconformal index diverges. So one needs to be really careful of how we take order of limits. If one looks at the first order of limit, we just get back the Schur index where we take t goes to q and then set p equal to 1. In principle, we could have set p arbitrary because the Schur index is independent of p. But then if I chose a slightly different parameterization in the PQT space, t goes to qp and then p goes to 1, this is not at all the Schur limit. This is something entirely different. To convince you of that, one could do an explicit calculation. For example, if one took the index of just free hypermultiplets and did the first thing, one would get some non-trivial theta function. But if one used the second limit, in this limit, one can explicitly check that for, say, free hypermultiplets, this limit trivializes, and the index is just 1. And similarly, if one computes these two limits for vector multiplets, again, these two limits are different, and in particular, the second limit for the vector multiplet completely diverges. So, yeah. The divergence is because p goes to 1.
So there are operators that are unsuppressed.
Yes.
When p is 1.
Yes.
Unsuppressed by what kind of operators? What charges?
One could. I don't remember the exact form or the conditions that they satisfy.
Yes.
Okay. Yeah.
So omega goes to.
Right. Yeah. So yeah, basically what I wanted to convey here is that the order of limits is really important, and to sort of use utilize this order of limits issue, many people try to define a more generalized Schur limit, which was actually first defined in this paper almost 10 years ago, where t goes to qp to the 1 minus alpha and then p goes to 1, and also in this in a more mysterious form in Deb-Razamat, but these two limits are essentially the same. So we'll try to see what the Schur index becomes when we take this particular limit. So yes, it does. I'll explain that then. Thank you. Yeah. So let's first start with the form for the general superconformal index, and you can always write it in terms of the integral over the Cartan variables, and then and the index just for the single letters, and then take the plagistic exponential of that. That's standard stuff. And now in principle, what one can do is just take the limit of the single letters, and then one would get a generalized single letter indices for both the vectors and the hypers, and one can easily calculate them because we know these we know how these behave for arbitrary p, q, and p, and these are given like this. Now putting these back, one obtains a simple formula like this, but Shiraz, you were asking for something that's concrete and finite a few days ago, but unfortunately this is concrete but not finite unless you regulate this. So how Deb and Razamat choose to regulate this integral is, so if one examines this and puts alpha equal to 1, one can easily see that it reduces back to the Schur index, and there are no divergences appearing from anywhere because we are not really probing those operators, which all the derivative operators, and but one can just check that for any other value of alpha this diverges. So yes, okay. How I got this sort of scary looking equation is just by putting these two these can be just calculated from first principles because we know what these are for general p, q, and p, and then I just take the limit, and then now I just substitute these back into the main formula, and I get this back. I just do the this power, yes, directly from this calculation, with the caveat that there's an infinity sitting in front.
It's so weird, right? We normally get stuff, but not stuff to amount.
Yes, that's because of, okay, let me give you an example. Let me tell you how the denominator to the alpha comes about. It comes about because there's an alpha sitting outside here of the full single letter index. And then taking the plagistic exponential of that just gives us alpha to the whole, the expression to the power alpha. And one could just go through the calculation and convince yourself that the entire integrand that usually is not raised to any power is just now raised to a power alpha. Okay, so how are we regulating the, okay, how did Deb and Razamat regulate the divergence? They said that, okay, for alpha equal to 1, there's no divergence and it reduces to the Schur index, so there's no problem. And for alpha equal to 0, which was actually the same limit as the second limit over here, because putting alpha equal to 0, we see that t goes to qp. This would correspond to being at a generic point on the Coulomb branch, where, okay, yeah, I sort of skipped through many steps, but you see that the divergence actually comes from the vectors here. Explicitly the divergence comes about because for any value of alpha other than 1, there's a constant piece sitting here, and the plagistic exponential, which is also given here, of a constant function is just divergent.
So you've taken that outside.
I've taken that outside.
So it's not a divergence, it's just separate.
It's just a separate divergence, yeah. which one can choose to. It's basically like 1 over 1 minus 1 to the rank of the gauge group. That's the divergent piece that sits outside. And you can just put these back and follow these definitions and see where the divergence is actually coming from. Yeah, and how is that regulated? We can regulate it by asking what should this quantity be when alpha equal to 0. When alpha is 0, the theory is at some generic point on the Coulomb branch where you've turned on some webs for all the Coulomb branch operators, and the symmetry is generically broken just to a u1 to the r, where r is the rank, and there the Schur limit of these symmetries, it should just be the q-poke hammer to the 2r, and so that's how we can fix what quantity sits outside. And these q, the q to the c 4d over 24, I've just inserted them so that this will later be useful for modularity of this object. But in principle, these are not, these need not be here. Maybe let me pause here if there are any more questions regarding the limit or how these arise. Yeah, I just put it in by hand. Well, you can consider it as Casimir energy, but usually whenever these indices are calculated, 4D people tend to ignore that. So, yes, yeah, exactly. So, okay, so let's proceed. Okay, if one looks at this really scary integral, even after discarding the infinite factor, this is the integrand is basically a ratio of infinite products both in the numerator and denominator, and one has to compute this, and it's very non-trivial to do this because this is not like just computing the residue theorem, especially when alpha is a arbitrary real number which is positive. Say for example, say alpha is half, then computing this becomes very tricky. And what Deb and Razamat found a few months ago is that this index or the this generalized Schur partition function satisfies some really interesting properties, namely that whenever one takes alpha to some specific rational values, it matches to the Schur index of a completely different theory. As an example, one can just take the simplest n equals 2 theory, SU2 with 4 fundamental hypers, and then put alpha equal to 1/5. Then this scary looking integral just gives us this very probably one of the simplest Q series that we've all seen, and this actually corresponds to the Schur index of an Argyris-Douglas theory, which is also has an associated 2D VOA, which is just the 2,5 minimal model. So, and in principle, this should be really surprising because first, for when alpha equal to 1/5, one is really computing this very big integral, but all of these integers, just all of these functions which are in principle functions of alpha, just all turn out to be integers. And this was observed not just in sporadic cases, but they show that you can actually reproduce an entire family. The family that was actually first found in the MMS paper, the Deline, all of them are positive, yes. No, even though this is like a limit of an index, all of these are positive. And that's generally true when you compute Schur indices of many theories. Yeah. In principle, I can show for what values of alpha you will actually have negative. So, yeah. So, in principle, you can obtain an entire family of theories just by starting with the SU2 and F equal to 4 theory, and by sort of scanning around for different values of alpha, and you reproduce all of these other 4D SCFTs. Or when I reproduce, I mean you reproduce the Schur indices of all of these other theories just by doing a computation in SU2 and F equals 4. So this was one of the surprising features that they found in their paper, and by found in their paper, I mean that they tried to compute these numerically, and it was a difficult computation because for the integer values, the calculation is reasonably easy, but numerics when alpha is fraction tend to get difficult, especially if you want higher powers of Q to really check if the final object that you compute is modular or not. So so these the numerical observations of Razamat and Deb they naturally raise two important questions. Can we actually analytically show that this generalized Schur partition function is equal to the Schur index of a different CFT? That's one question where you could try to answer, especially given that these integrals are hard to compute till arbitrary precision. And also there's another question: why did these theories show up, and why not some other 4D SCFTs? That's another question maybe you would like to answer. Which theories can you actually reproduce by just tuning alpha? And we'll see that in the next 10-ish minutes that both of these questions are actually answered by modular differential equations. Yeah, in principle, we believe that this would hold for any generalized Schur partition function, not just for SU2. We have results whenever G belongs to the USP2N family, which also includes the SU2.
Sorry, one more general question. You're taking basically a limit where derivatives are unsuppressed. It's like a high temperature limit.
Yes.
Is this somehow related to this Cardy limit that people have studied before of the superconformal index?
Probably not, because in the Cardy limit you usually encounter both the A and C central charges in 4D. But here I don't see how you get the A4D out of this computation anywhere. But
so the Cardy limit also barely suppresses derivatives, right? So it feels there should be some. Okay, thank you.
Does the energy factor?
Does the what? Sorry.
Does the matching, the identity that you get between a superconformal index, the Schur index for the alpha non?
In principle, yes, because we can start with the original definition where we've put in the Casimir energy. Like when alpha equal to 1, we know what the Casimir energy is, and then for whatever alpha you want to tune this object, you will know what you will actually get a different C4D, which will in principle depend on alpha. So in that sense, it's an output of this calculation.
So you also get the central charge right of
these theories, yes. For example, whenever we tune alpha, we get all of these central charges right.
Okay.
So,
is there a unique theory for any specific value of alpha, or you can have 2-3 theories?
Yeah, this is a good question. It slightly depends on conventions. If one fixes, okay, let me put it this way. In the usual Schur view correspondence that Sunil talked about, these Schur indices always correspond to identity characters of usually non-unitary theories. So if I always call whatever the Schur index computes as the identity character, then yes, whenever as we fix alpha, it always gives me just one answer. So, okay, let me go ahead. I'm very lacking time. Yeah, so these are the two questions we would like to answer, and I'll first state the main theorem, main statement that Sunil has already stated, that the generalized Schur partition function with now alpha analytically continued to all complex numbers. It satisfies an MLDU of fixed order whose coefficients all depend on alpha. And we'll first show it for the simplest case of SU2, where, as Sunil mentioned, it satisfies the MMS equation, where mu is clearly determined in terms of alpha. Now, the proof of this, I will state the proof in 3 simple steps. First, for the case of SU2, we go back to this the general scary formula and then specialize this to SU2, where we know what the non-zero roots and weights are, and then we have these infinite products both in the top and bottom. Now these can be rearranged and we can identify that those infinite products actually rearrange quite nicely into theta function, and in fact such theta function integrals of theta Jacobi theta function representations for the Schur index have been well known over the last few years. This is the starting point of our proof to show that this object is actually is a vector valued modular form, and the strategy is first use theta identities to further simplify this integrand. We've already simplified it a bit. And second, use Jacobi elliptic functions to again simplify it further, and then and do a final change of variables to match it exactly to the RCFT contour integrals that Sunil talked about, which were invented 36 years ago. And thank you. So Z is related to U as just e to the 2 pi IU in a standard elliptic variable. Okay, so let's first go through step 1. This is a ratio of theta functions with the odd theta in the top, but it has 2u now instead of u. This can be easily simplified by realizing that there's a doubling identity for theta functions, which is stated here. I'm flashing that here. And now the integrand, just by substituting this back, can be written in terms of ordinary elliptic theta functions with all u's instead of 2 u's, and where I've used that these Jacobi thetas and eta are also related, so this factor clearly cancels out. Now I use Jacobi elliptic functions, the SN, CN, and DN functions, and I think these have already made an appearance sometime maybe in Shailesh's talk couple of days ago. And these are just the elliptic generalization of the usual trigonometric functions with an elliptic modulus, where when k goes to 0, these reduce back to our usual trigonometric functions, but when k is not 0, these are doubly periodic functions, and they can be expressed in terms of theta functions, and that's exactly what I did here. From the previous slide, I rewrite these theta function expression for the integrand in terms of the Jacobi elliptic functions, and here the parameter now is mapped to a different parameter here. Initially, u was related to just e to the 2 related to z via e to the 2 pi iu, but now the parameter in Sn, Cn, and Dn is v with a rescaling that's dependent on tau in this way. And now we are almost done. I again define a new variable t, which is lambda Sn squared v, and by just almost miraculously the integrand the really scary integrand with infinite products just simplifies into a polynomial in t. So and putting this back into the integral, we get back and also including the measure factor, we get back the integral that Sunil was talking about, and also the contour surprisingly matches exactly. Thanks. And the contour matches because of the periodicity properties of these elliptic functions. Okay, so probably this was a lot of this calculations in algebra, but let me just state something, that these change of variables is very natural from a mathematical point of view. We performed like a long chain of variables, but essentially t lives on just a complex plane with these 3 branch cuts, or on the sphere with these 4 branch cuts, and this map that we use, that t was lambda Sn squared, is essentially just the double cover of this to the torus. So, and this fact is very well known in mathematics. So that basically concludes the proof that the generalized Schur partition function that was defined by Deb and Razamat is actually modular, and you don't really have to do numerics, but you can essentially by this really nice change of variables, you can prove that it's a modular quantity. Now since you know that it's a modular quantity and it actually solves the MMS equation, you can ask, does it correspond to characters as we change alpha? And the initial table that I showed with the list of 4D SCFTs now actually makes a lot of sense. And from the exponents over here, you can actually even calculate C2D, and that's just given by these minus 12 alpha minus 2. And you can see when alpha is always positive, it's always this quantity is always negative. But in principle, you could this now, since we have an integral form, and in fact this is nothing but a 2f1. It's a very simple function. You can analytically continue alpha to whatever you like, and in fact even negative. And we would encounter unitary theories, logarithmic theories, and in principle even quasi characters which have negative integers in them. Okay, so this was for the case of rank 1. The same story goes through for higher rank, but only for the case of USP2n. And essentially you will repeat the thing with multiple parameters, and then there are extra terms which you can show that they nicely map to the van der Waals in the t variables. So that all works out very well, and then you can find examples for this. Since I don't have much time, let me not stress more, except for the fact that again, by taking specific rational values of alpha, you reproduce many different known 4D SCFTs which correspond to known 2D VOAs. For example, again 2, 2n plus 3 minimal models for the case of alpha equals 1 over 2n plus 3. Okay, or maybe let me skip this. So once I've shown that this can be written down in terms of this, now by analytic continuation I can take alpha to be negative. Yeah, exactly. Yeah. Yeah, so in principle you can do it. I mean, if the goal is to prove that this object is modular, one could try to just brute force it somehow by applying this change of variables for any group. But now comes the fact that in Sunil's work from 36 years ago and even later, they've written down contour integral forms for only a specific set of, though an infinite set of CFTs, but only a specific set. And if we try to find what this generalized partition function for other groups is, it so happens that it doesn't lie on these families. Oh, I just put all the flavors to one. Okay, that's a good question. I think it does go through. This we have not proved analytically, but we can check that even with flavors, it is modular. Yeah. Right. Right. Yeah. I see. This is interesting, something I've not thought about. But yeah, in principle, one could try to do the same computation with the flavor fugacity also added. But maybe we should talk about this. No, they've had a paper recently, or again last week, where he does some numerics for this, but nothing analytical. Okay, so let me just quickly go to the last part of my talk, where I'll try to state a conjecture. Now, it's a very famous known result that the Schur index is actually related to this, the BPS monodromy matrix, sometimes also called the Kontsevich-Soibelman wall crossing invariant. And this can be constructed in a very abstract way with non-commuting formal variables. And the crucial part is this can be constructed only using Coulomb branch data. And this is known to be equal to the Schur index whenever we take the trace of M inverse of this, where this trace is defined in a very formal way. But this is a very famous formula, because on one side this uses only Coulomb branch data, and the Schur index is something completely different. Now, another interesting fact about this BPS monodromy matrix is that one can try to take powers of it and also fractional powers of it and compute the trace of it. And it has been seen in at least many examples that this also produces characters of rational theories. And motivated by our analytical results, we just conjecture that for any arbitrary k of the monodromy matrix, this expression with where the central charge C of this theory would be given by this also satisfies an MLD of a fixed order. So this would be a conjecture for directly starting at so k here is could be an integer or a fractional number. It's something like the analog of alpha, or yeah. So it would be really. Yeah, exactly. So yeah, it should be minus. So if you put alpha equal to 1, this is, so k is roughly like minus alpha. Yeah. Okay, so that's the conclusions. The main technical theorem is that these generalized partition functions solve MLDEs, and the proof is pretty much simple. It's just a standard change of variables that is well known in mathematics. And we've been able to show this only for a specific infinite family, the USP2N series, and it would be very interesting to show this for generic groups, because numerically one could try to check that this is true at least to a certain order, but an analytical proof would be much better. Yeah, let me conclude there.
Any questions?
You said something about for some specific value of alpha where you have integer coefficients, you map this thing to some rational CFT of two character rational CFTs, right?
Right. Yeah, for example, this.
Yeah, but do you have like a general like? Can you map to some arbitrary character RCFTs? Like, is there a?
Yeah, you can. For example, if you start with say a rank on 4DS CFT, especially this one, you can only map to a two character one. But starting with say the USP2N series, you can map to all the 2, p minimal modules.
Okay. Okay.
Ajay.
You have a divergence in some limit.
Right.
Is that a pole? Is that
Okay, let me go back to this formula where the divergence should have been. It's definitely not a divergence in the z variables.
Yeah, it's divergence when something goes to.
Yes. Yeah.
Is it one?
It is like that. It's
1 over epsilon where?
It's literally like 1 over 1 minus p to the r. So that's pretty much it.
Very similar to because we had told that divergence.
Yeah.
And it's the same limit.
Yes.
Because you're taking mu goes to the.
Yeah.
Find that. So I think something supersymmetric version.
Any other questions? Okay, I don't see any other questions. So let's go for tea break, and we will meet at 11:30 in 15 minutes. Yeah.
The relation was alpha equals minus k, right? Yeah. Positive powers of negative powers of alpha.
There are two mics, this and this. But this works. That's
Okay. Okay, yeah, please be seated. Okay. So welcome everyone for this second session of this morning. And our speaker now would be Giuseppe Policastro, and he'll be telling us about interfaces in TT bar deform 2DC.
Thank you very much. Start by thanking the organizers for inviting me to participate in this very nice meeting. It's my second time actually in the Indian Street meeting. The first time was also in, well, it was in Puri more than 10 years ago. So today I want to tell you about this work which we put on the archive last week with Avik Banerjee, who is was a postdoc in Paris. He's now doing a postdoc in Warsaw. And there is some previous work on which this is based on, starting from 5 years ago, about interfaces in CFT. So this is the outline. First, I will recall some facts about CFT interfaces and some properties of these interfaces related to the energy transmission. Then I will remind what is the TT bar deformation, why do we study it, and finally our results on the interfaces in this deformed CFT. We are used now to the idea that if we start with some system, which could be, say, a lattice or anything, and if you are interested only in the long distance properties, then sometimes or often we can end up in a low energy long distance description. Can be some sort of CFT, so a critical point of a condensed matter system, and the RG flow is the procedure that formalizes this intuition, and it tells you that so the CFT captures some universal properties of the system, in the sense that there are some microscopic details that don't matter, but different systems that differ in the microscopic details can be described by the same CFT, and this is what is called universality in the statistical mechanics sense, and this is captured by some data of the CFT. So it's like the dimensions of the scaling dimensions of the operators, the OP coefficients, the central charge, for example, in a 2D CFT. Now the same applies if we have, say, here we have a perfect lattice. We start with a lattice that has some defects. Now in the UV there can be several different types of defects, but similar logic will tell you that when you flow to low energy, you have a defect CFT, and so you retain some information about the fact that there was a defect, but you have some universality class of defect with some universal data which characterize the defect, and this defect will flow typically to a conformal defect. So there will be some part of the conformal symmetry which is unbroken. And so an interesting question is how to characterize the defect. What are the universal data that you need? So this is from a say statistical mechanics point of view. There are also other reasons to be interested in defects. There are special types of defects or topological which encode the symmetry structure of the system. So if you have an object, say some point-like or extended object in the theory, then a defect can wrap or link around the appropriate codimension, and the action of this linking can represent the action of some symmetry, invertible or non-invertible, depending. But it's the most general way we can understand now to see the symmetry of the system. Also, there is some quantum information aspect. If you have a weak measurement, you have a spin system, you perform some weak measurement by coupling to some auxiliary system and measuring them. Then in the continuum limit, sometimes you can also describe this as a defect that is a spatial defect. So it lives on a fixed time, say on the whole system. There have been some recent work done on this aspect, and so you can use defect CFT techniques also for this problem. And so it's important to know how defects behave under RG flows, because that allows you to put some constraints on the UV theory by knowing what defects they can have in the infrared theory. So you can access some UV properties by looking at the low energy if you know how it behaves under RG flow. But usually it's quite difficult to exactly. So yeah, so that's the motivation for studying conformal interfaces. So defect is more general, but an interface is a defect of codimension 1, which you can use to join two CFTs, say on the half plane. You can also fold the CFT left on the right and turn the defect into a boundary. However, the boundary CFT that you get is not a generic CFT, but because it has one additional spin2 operator, a kind of a relative stress energy tensor, which is orthogonal to the stress energy tensor. And so even though it's a BSFT, still the fact it's a defect has different properties from a generic boundary state. So what characterizes a conformal defect is this equation that follows from the word identity, or it can be reformulated as the fact that you can see the defect as an operator that maps the CFT state on the left to the CFT state on the right, and this has to commute with the action of a subgroup of the Virasoro left and right. So I'm studying only to be CFT. So this has to intertwine the action of the Virasoro on the left with the Virasoro on the right. So if you look in the CFT without defect, as I said, in the universal sector of the stress energy tensor, there is only one piece of universal delta, which is the central charge. So what happens when you have the defect? So the central charge appears, for example, in the free energy of the theory. If you put it at finite volume or on the cylinder, it's governed by the trace anomaly. So if you have the theory on the cylinder, you have the entropy, say it's proportional to the central charge times the appropriate dimensional factor. If there is now a boundary or an interface, in this case it's not different. What you get is additional pieces, some boundary entropy, also called the G factor, which was introduced by Affleck and Ludwig and has been studied a lot. And so this is a kind of manifestation of, or a piece of universal data associated to the interface. The central charge also appears in the entanglement entropy from the Cardi-Calabrese formula. If you have now an interface, we can also look at the entanglement entropy. You can see actually there are different cases. If you take the interval to be symmetric around the interface, then again you have this log G factor. But if the interval is asymmetric and is touching the interface, you get also an additional modification of the central charge. So, so again, the same piece of data in the bulk now gives rise to two different information: the G factor and also the effective central charge. And there may be more manifestations. We haven't exhausted all of them, but one is is there a question? One that is important is also the central charge appears in the two-point function of the stress energy tensor. Now in the interface, basically the object which is analog to the stress energy tensor is the displacement operator, which is the response to the displacement of the defect. So if I put the defect along a line X, and then I change the location, then the response is this displacement operator. In 2 dimensions is nothing but a certain combination of the stress energy tensors on the left and right, and this appears in the OP of the not the OP, the conservation. The word identity for the stress energy tensor is modified because the defects break some symmetry, so there is this term, and this equation tells you that the dimension of the displacement is protected, so the 2-point function is fixed up to coefficient. Again, a different coefficient that appears because of the interface. And this can also be read from the OP of the bulk fields, so the stress energy tensors left and right contains a new coefficient, this C left right, which is related to the 2-point function of the displacement in this way, so they are not independent. So yeah, we have these three data that characterize the interface. Now this C left right is particularly interesting because it has the interpretation of energy transmission at the interface, as was recognized in this early paper. They found that this particular combination of correlators of the energy stress energy tensor, which they call the reflection coefficient, and is related to the left-right central charge in this way. Well, they just brought it down and found that that it satisfies some bounds that follow from unitarity. So it's bounded above from 1 and below from this difference of central charges to the left and right. A better interpretation was given on this paper a few years ago, which studied the Lorentzian picture. So they put the CFT in the Lorentzian signature. The defect is the interface is at fixed position and it lives in time. And now in this picture you can talk about scattering. Of course, CFT does not have particles, but you can create a sort of scattering state by inserting an operator, taking it very far away in the past or very far from the interface. Then you look at the excitation that it creates, and when it reaches the interface, it can be reflected or transmitted. And using the ANEC operators, so the integral of the light component of the stress energy tensor, it basically has the interpretation of collecting all the energy flux, which is transmitted or reflected. It's independent of you because it doesn't depend on you, so you can put it on any light like. If you put it at infinity, you can see that it will collect all the transmitted energy, and then you can define this ratio, which you have to show it's well defined. This limit exists, and it defines this transmission coefficient. And then they found that it's actually is the same that was defined here. Although here it's on the end, this R is the average, and here you can define two independent left and right transmission, a priori independent, but actually they are related in this way. And now one interesting thing is that by positivity of ANEC, you get some bounds on R, but these are not the same as come from unitarity. These are stronger bounds. The same we saw in Shiraz-Stock, that ANEC, positivity of ANEC can be stronger than unitarity bound. I think it's something that is not completely understood yet. And so this translates into some bounds on the left-right central charge, which has to be smaller than the bulk, both the left and the right central charge. And one important property of this study was this universality, now in a stronger sense, not in the statistical physics sense that I talked before, but in a stronger sense, that this transmission is independent of any details of the incoming excitation. In particular, independent of the operator which creates the state, which is surprising if you think about it, because it's not a typical situation in a normal interface. It may depend on all sorts of details of the system. Mm. Yeah, this is similar to how you derive that the central charge in a unitary theory is positive just by looking at the two-point function, finding a particular case when it's a norm, right? And then it has to be positive. Here it comes from. No, it's still two-point function, but you have to use a matrix because there are different t's left and right. So you have to find the particular matrix, combine this. No. So you're talking about this bound? This... So this bound, yeah, I understand you are talking about 2 points, but the next one, like by Oh, yeah. How do you derive this? Yeah, this 3-point function. Like this, this bound training, then the 2-point function, right? So there you use only the unitarity of 2-point function, and here you are kind of implementing from 3-point function. So it's not possible to start writing the daily for a more strong account. Yeah, in a sense, it's true. So that there is, but ANEC ultimately is also a consequence of unitarity. So it's just that what I want to say is that when you say unitarity bound, it's just used as a certain corner or simpler manifestation of unitarity. This goes a bit farther, but probably you can go also farther. We don't know the full extent. Similar to what they do in the bootstrap, you try to get the full extent of the implications of unitarity. We don't know how to do it in a systematic way in this problem. That's for the question. Right. So yes, and also this has the implication that if the two CFT don't have the same central charge, you cannot possibly transmit all the energy from the theory with higher central charge to the one with the lower central charge. So this is also a striking implication of this bound. So in CFT, okay, you cannot do very much in general. You can study the free case or some rational CFTs, which has you cannot classify all defects in between two CFTs. Even in the case of free boson, it's not known what is the most general conformal defect. So to make some progress, we can go to holography, where we have this simple model, minimal model for the interface, given by a brain extending in the bulk with satisfying Israeli matching condition. You find that once you impose the matching, there is a single parameter, the tension of the brain, which fixes the full geometry, and you have a solution which is stable only between certain bounds for the tension. And in this earlier paper, we computed the scattering setup of Maineri in the holographic way. We perturb ADS3 with webs of the stress energy tensor by asking that there is only an incoming and reflecting wave on the left and only transmitted on the right. Okay, there are some details that I'm not going into. The only thing that I want to say here is that by imposing the boundary conditions on the fluctuations of the brain at the boundary, this has the condition that imposes that R plus T equal 1, which is what you expect, and that it will be important later. And also we get the formula for the transmission coefficient in terms of the tension, and we can verify that if we stay within the Anek bounds when the tension is within the gravitational bounds, which is satisfactory. However, so for C left equals C right, there is no lower bound, but there is still an upper bound. Just from CFT, the upper bound will be only 1. But in holography, we can only reach R equal 1/2. So you cannot have perfect reflection with the brane. If you want to have total reflection, this can only happen in this limit when the central charge goes to 0. So if you want to go to the BCFT as a limit of ICFT, you have to have infinite tension. Same results can be also obtained by looking at the non-equilibrium state by trying to join two PTZ black holes. So if you have a hot black hole, say, and a cold one, and you try to make an interface between them, you find this solution does not always exist. So the brain sometimes wants to turn back the bulk and come on the boundary again, which is not what you want, because then you have two interfaces instead of one. So you have to tune so that there is only one interface, and require regularity of the solution then fixes basically the flux in terms of the temperatures of the two sides, which in turn can be used to rid off the transport coefficient. So this is a brief recap of what we know about the CFT. And as I said, we want to understand how defects behave under RG flow, but this is hard. But the way to move away from conformal invariance is to use the TT bar deformation, which is nice because it's exactly solvable. I should mention there is also another way that we have studied with Ayan to break conformal invariance. He will talk about this in his talk tomorrow. It's a very different story. But so here I will talk about this deformation. It's an irrelevant perturbation of the Lagrangian by this operator TT bar minus trace squared. It has been studied a lot in recent years because it is exactly solvable. If you have an integrable hierarchy, this will be preserved by this flow. If you put the CFT in finite volume, you have an exact expression for the energy states, which you can compute. If you know the unperturbed spectrum, this gives the exact deformed spectrum. And it has this property that depending on the sign of the deformation, either you have complex energies for some states require complex energy, or if mu is positive, then there is Hagedorn growth of state, and you have a non-local UV theory. Now it's important that this it can be often the leading irrelevant perturbation if you perturb around the UV NIR fixed point. And so this will give some information about the RG flow, at least not too far away from the critical point. So it's like a first order information about the RG flow, which we get the other way around by following going up the RG flow instead of down. So what is important also is that this can be realized as a dynamical coordinate transformation. So by putting the CFT in a deformed geometry. This deformed geometry is, however, state dependent. So it's, diffeomorphism is defined by the state, or more precisely by the expectation value of the stress energy tensor in the state. And these equations basically tell you that the particles experience a delay in the scattering, which is dependent on the energy and momentum of all the other particles in the system. In a CFT, there are no particles, but actually this is more general. It can be also applied to non-relativistic systems or anything. So this can be used to derive some equation for the correlators. You can see how the fields flow under the deformation in this way. And if you restrict to the leading OP singularity in this product, you can resum, and what you see is that these particles start diffusing with the diffusivity which is proportional to the deformation. So so particles start being pointless in the CFT, in the theory, under form theory, but then they acquire a finite size under deformation. So things don't want to stay localized, which you may think that also a defect. If you put it in the theory, you will not want to stay localized, but that's a naive expectation. And holographically, there is a prescription, or there are two prescriptions rather to deal with this. So you take the IADS3 in Fermat-Graham expansion, and you deform the dictionary by defining the boundary metric to be this combination instead of just the leading term, and the stress energy tensor to be this combination. So if you are in pure gravity, then actually this combination, you can see it's just the induced metric at a certain radius. And so these prescriptions are equivalent to just like putting a cutoff at a finite distance for mu positive, but they are the equivalent. And you want to be in the semi-classical regime to have the finite cutoff, which means since you send C to infinity, you have to send sigma to 0, keeping sigma C fixed. So we work at small deformations, basically, the large C limit. So this will say it's a semi-classical regime that we are interested in. In the semi-classical regime, these flow equations can be shown to hold for the expectation value of the stress energy tensor, which follow from this prescription. And because the flow equation preserves the flatness of the metric, if you start from a flat undeformed metric, you will have a flat deformed metric in new coordinates. And so this you can use basically to solve the system at the semi-classical level when there is no interface. However, this change of coordinates from U to capital U would generically change the position of the interface, and so this will not help, you would think, when you want to study the interface. But actually, it still helps because you can correct for this deformation by using a conformal map in the CFT. So you start from the CFT undeformed, but you have to start with the defect, which is well, you start from the straight defect, but then you have to deform it with a conformal map in such a way that after the TT bar deformation map, it comes back to be straight again. So this will impose some equations for these parameters of the conformal map that have to be tuned to the stress energy tensor in the undeformed theory. And this is the change of coordinate that implements the TT bar deformation. So you can solve this. And you have 4 functions, 2 on each side, and 3 conditions. 2 come from imposing that the defect it stays where you want it to be, and 1 other comes from imposing that the time coordinate is continuous and the interface. And there will be 1 unfixed function, but this gives a check of the method that the physical results will not depend on this unfixed function.
Yes,
basically,
you have 3 more minutes.
3 more minutes.
Yeah,
Okay.
So okay, you have to invert the equation, but you cannot do it in general. There are 2 cases where it can be done. One is the non-equilibrium steady state, because in this case the stress energy tensor is constant, all the components are constant, and this Schwarzian piece vanishes in this case. So this simplifies, and basically what you have to do is you follow the solution along the shock waves, as Amos talked about this Monday, and this determines the initial conditions, or the matching conditions from the initial state to the next state. So this is a picture of what happens without the interface. Basically, you have this. This defines the next state. Is just given by this piecewise functions for the stress energy tensor, which define the initial condition, but then actually define the metric everywhere. And this theta function just describes the shock waves. In the deformed theory, they propagate along some modified light cone, which you can determine exactly. So the upshot is that after everything is done, then you find that the interface matching conditions become nonlinear. So you can still define the interface, but the transmission coefficient is now replaced by a transmission function. So you have these nonlinear corrections to the transmission coefficients. These functions turn out to be antisymmetric. So it's a function of the two incoming fluxes. It's fully antisymmetric. You can determine it order by order, and basically this universality of the energy transmission coefficient is replaced by the universality of this function. But these coefficients are just a universal function of the fluxes. This universality is even more apparent when you go to the scattering of waves. Now in the CFT, different frequencies don't interact, so the problem is much simpler. But in the deformed theory, you have interactions, so you have to consider what happens when you superpose states with different frequencies. But this we can do only at linear order. So at linear order, for a single frequency, we can repackage this as a frequency-dependent transmission coefficient. We find this result, and it stays within the unitarity bound only for certain range of frequencies. Importantly, the same for both signs of mu. And for any value of the underformed transmission, you always get all values from 0 to 1 as you change the deformation parameter. For a superposition of frequencies, you cannot write like this, but you can rewrite it as a series in the time derivatives. And again, you have these coefficients which are universal, but now depend also on the time derivative. So then here we start seeing this delocalization of the fields that we expected. If you go to quadratic order, it has to be more complicated because you have to include explicitly the effect of the trace, and this is a work in progress, so I cannot tell you for the moment. And last thing, so I told you in the CFT, when we impose the boundary conditions, you immediately get the R plus T equal 1. Now in the deformed case, you get two conditions actually from this. One is the same, but also imposes this relation of the deformation parameters with the central charges. They have to be the same. And this is natural if you look at the cutoff prescription. This is just saying that you have the same cutoff on both sides. However, we don't use actually the cutoff, but the modified boundary conditions. And now they are not the same because it's not pure gravity. We have the brane. And it's a bit different if you impose the cutoff at 0 or at mu as defined. So it's important that we are using actually this modified boundary prescription. So okay, this is I'm stop here and thank you.
So in this TT bar, you get the nonlinear relation between the reflection transmission coefficients, but the quantum map has to be linear, right? I mean, this from is as a map in the Hilbert space. So how do you reconcile this in the operator formalism?
The map has to be linear. Yes, that's a good point. I think this will be well, the underlying quantum map should be linear, but this is an effective resummation, I think, of it applies to this NES state. So it cannot be taken as a quantum statement, operator statement. But yeah, I don't know exactly how to.
Yeah, like in a Nambu-Goto case, we have a way to understand it, but
yeah, I don't know exactly.
Okay, thank you. Thanks a lot for the organizers for having me here and giving me the opportunity to talk about something which I have actually talked about in various forums, but not in ISM. And just to paraphrase for me, one should never underestimate the pleasure an audience derives from listening to what they already know. I'll proceed with this. And I chose the title kind of inspired by Louis Carroll, who said that we should be able to think about 6 impossible things before breakfast. And this is the same Carroll, incidentally, whose name is now being taken in various conferences, in the Carroll limits and so on. So I hope I will have some sympathies from them as well. So what I'll try to tell you about is let me first declare that I'm actually kind of going to heavily suppress all the calculational details explicitly. So if things don't make sense to you, I mean what exactly is being done, etc., please feel free to ask me. But what I decided to talk about is actually a couple of results, couple of impressions that I seem to have over a few works that we started with these people here, especially with my Shumon, who's now going to move to Europe, and Chetan and many others. And it's really my collaborators who kind of, I think, drove me more into this. Initially, I really was I had a lot of skepticism. I still do, but at least I think there is something interesting that is going on. So I'm just here to share that with you. So I'll start with this picture. It's a good picture to have in mind. It's an old picture. There are better resolutions. So this is the black hole. This is the picture of the black hole, literally the photograph of a black hole. And this black circle here is basically the horizon, the event horizon. At least that's what we think it is. And then it comes. Then immediately you ask these questions where, are there? What is the physics at the scale of the horizon? Whether there are things, whether there are structures, quantum structures, or otherwise. At the black hole, or whether this is smooth, and so on and so forth. Questions that anybody who's interested in quantum aspects of black holes are really interested in. And this is a difficult, so let me just write, to my understanding, current technologies cannot really access what is happening with the physics at the horizon scale. But I think it's also interesting to keep these numbers in mind. It's quite impressive that this is the length scale at which we can now probe. Actually, it can go even a few order more. But of course, what we want to know about is about the quantum scale, which is still a few orders away. But still, I think it's seeing these numbers kind of helps me. I mean, I don't know about you. With that, let me start with already I think impossible things that people try to understand in understanding black hole physics of black holes. And by impossible things, I really mean things that we perhaps don't understand in their complete details, but they're nonetheless very interesting. And one approach is just you look at essentially some version of the Gibbons-Hawking Euclidean quantum gravity, and that is supposed to, and that does give us some fine-grained information about what is happening with black holes and so on and so forth. And there's a lot you can do, not just thermodynamics. Very recently, people have done a lot more with finer-grained information, such as entanglement and so on. And this is a very, very interesting field of study in itself. There's another way of thinking about it, which is, I guess, more fuzzy or fiery, where people say that there are actually structures at the horizon scale, and the idea there is to, because we know string theory, we are supposed to be able to build this microstates and then eventually count them and see the black hole physics come out of it as an average and so on. And this this goes under the name of fuzzballs. And there are lots of things that go around technically or conceptually, which I find at least very interesting. But this is also a very, very complicated thing. I mean, it's also almost impossible to think about that you are actually going to count all these things and average and show that exponential of entropy worth of microstates to be found out explicitly. And also, there's an impossibility with the Euclidean quantum gravity approach, which is, kind of ill-defined from the beginning. There are, of course, also other approaches. I'll talk about none of this, just to sort of for completeness, which hopefully can be captured with these phrases, smooth horizons and mirror operators. But that also has certain impossibility tied to it in terms of, changing quantum mechanics a little bit. But anyway, I will have none of this to talk about. What I will have to talk about is well, the impossible thing for now is going to be whether we can have boundary conditions that give us interesting physics. And what I mean is really this question, that are there boundary conditions that result in non-trivial dynamics for an ordinary matter, and that even the dynamics that might look like what one would expect from a black hole. That's the question that I'm asking. And such as, for example, thermalization, decoherence, maximal chaos, and so on and so forth. There are of course very challenging questions here, and whatever I have to offer today should not satisfy you. It does not satisfy me at all. But it is. I just want to say that this is something interesting. At least that's all where I will pitch it basically. And just to sort of get going with this idea that, I mean, we do know that boundary conditions do give us certain interesting dynamics. I think one particularly simple example is really free particle. If I take a free particle, we all can, I mean, everybody knows, understands that in complete details. Yet when you take the free particle, subject it to a boundary condition, it becomes completely chaotic. So I think that's a remarkable example. It's a very simple example just to see that such a thing can happen. And if you want to be more sophisticated about it, then there are of course CFT states which are very special. The boundary states under quench, it can give thermal physics, and so on and so forth. So it's I should keep an eye on the watch. Yeah. So so this slide is just to say that indeed there are very interesting things that one can study. And in particular, for example, even for black holes, it is well known from the 70s that if you take these two-dimensional conformal field theories such as mirror models, they exactly sort of give you the black hole physics. And all you are doing there is no black hole whatsoever anywhere. All you are doing is you're just subjecting the CFT to some boundary condition, cleverly chosen boundary condition. That's it. And in some sense, you can ask, where did I get this boundary condition? I don't think that there is any answer to that. It's just the statement is that those boundary conditions are going to give you the physics that we see in black holes. That's at least to the best of my understanding. So this is going to be the picture. And I want to also say the following thing. This is again a phrase. What I'm about to say should literally be taken in the English meaning sense, that there might be a way to have some effective description of black holes, of quantum black holes, or some quantum aspects of black holes. And by this effective description, I do not mean in a Wilsonian sense. This is not an effective field theory expansion in any control sense or any such thing. But it is interesting to ask the following question, especially in the context of time dependent or non-equilibrium phenomena, because we do know that the Wilsonian Wilsonian sense of effective field theory description, if you involve real-time dynamics, gets a little bit subtle. So with that, let me give you the picture. The picture that I have, actually for very good reasons, I want to actually consider asymptotically ADS, although most of what I have to say, not what I have to say towards the end, but most of what I have to say now at least will be agnostic about the asymptotics. And then what I will do is imagine that you have a black hole here, like the picture that we started with. And what I will do is something that was done long time back by Thoft and many others, is that you can consider a certain amount, a certain fictitious and ad hoc wall sitting right in front of the horizon, and the distance between the wall from the horizon is a free parameter for me. So this is completely ad hoc and non-dynamical. I cannot justify why it should exist, but suppose it exists. And from some fuzzball kind of picture, you might, vaguely sort of motivate why such a structure might exist if you believe in a structure. But nonetheless, let's just go with it. And just as an aside, I think this kind of model has been recently explored, especially for in the community where people try to understand or see signals of LIGO and related stuff, whether they can distinguish between true black holes versus things that look like black holes. Yes. Yeah, it can be anywhere for me. Yes, that's correct. That is correct. But for me, I'll keep it. Yeah, for my purposes, I'll just keep it. I'll keep that freedom. As I said, this is not dynamical, so I'm not. By that, I'm just here. Yes. There wouldn't be any quasi-normal modes per se. There will be normal modes. Correct. So to
But if the Dirichlet boundary conditions are near enough to the horizon,
yes,
you'll have to wait very long.
yeah,
Just because that the time to see the difference as you go to the horizon goes
very long. Yes.
And so if you put it near enough, you won't be able to tell.
Yeah. So let me put it right out. So this is like particle in a box. You quantize a field, you get a normal mode, right? There is no quasi-normal mode. You can ask certainly. So this setup seems to me that it's completely it's going to fail miserably in giving me quasi-normal modes. But the point is that if you take this wall very close to the black hole and you compute the correlation function, like I mean ADS, that's why ADS comes handy, and then you look at the analytic structure of the correlator. The normal modes are poles in the real line, on the real line, and when you take this limit that the wall goes very close, the poles become dense, it becomes a branch cut. Then the jump is essentially what encodes the quasi-normal modes. So there is a way to recover the quasi-normal modes, but it's not through the yeah. Absolutely. No, but here I'm going to impose, as Sandeep said, Dirichlet boundary condition.
Yeah, but that's outside. You can think of it as inverse.
Yeah, that you can do. That you can. That is also yes. But I'm saying that if I did not do that, if I just stuck with the complete normal mode picture, there's a way to recover the quasi-normal modes also. That's actually very nice the way it happens. So one of the nice things, unexpected nice things that at least I could not intuit. So I should really this thing. Good. So this is the first impossible thing. So the first impossible thing is if nothing else, I mean this is the metric that I will secretly have in mind for the rest of my talk whenever I don't show anything. And then what you do is you just solve some Klein-Gordon equation in that metric. It's very easy, and the Klein-Gordon equation has to be subjected to some boundary conditions. So impose, for example, if you have ADS, impose some normalizability condition. But now instead of the normal usual stuff, what you do, this is the first impossible thing that I'm going to do, is impose some Dirichlet boundary condition without justifying any microscopic origin for this, and then one obtains the normal mode spectrum, unsurprisingly. And what I do here, sorry, I did not introduce this quantity, but let me just take 2 minutes to explain. So what I'm computing here is what is called spectral form factor. Those are nothing but the partition function evaluated at analytically continued temperature, and then you take the mode square. If you want to think about it in terms of more quantum mechanical, more familiar things, so if you take a quantum mechanical state, you evolve it with some Hamiltonian, and then after the evolution you can always compute what is the return amplitude, what is the probability of it coming back to the original state. If you take the thermophile double state, that probability is basically this quantity, the spectral form factor. And what comes out here, I'll just draw your attention that there's a feature which is called deep ramp and plateau, and this is thought to be a feature of a highly chaotic system. Although okay, let me come to the disclaimer later. So what is thought to be the highly chaotic thing is the following thing. So the fact that this thing comes, the spectral form factor, first of all, this is plotted in a log-log plot. So it starts from 1, that's just normalization, comes down to a point, and then starts growing up. So the point when it starts growing up is basically the point when the quantum, when the gap in the spectrum is started to being perceived. So this is the point where you start to see that the system actually has a discrete spectrum and not a continuous one, which and then eventually it plateaus at some point. And the plateau time scale is basically given by the smallest gap in the spectrum that you have. So if you had a continuous spectrum, this time scale would be pushed all the way to infinite. This is roughly speaking what happens, and this is the hallmark of, if you wish, a chaotic system. Usually people ascribe to such pictures to random matrix theories or random matrix universality classes. But what I described here is just a black hole, just a scalar field, a free scalar field in fact, propagating in a black hole geometry. So it's certainly not even interacting, and the resulting, even though this looks suggestive, it's not under RMT universality. That's something that is very important. But nonetheless, it does show this interesting ramp, and there are some details of this ramp which are also very close to what one would expect from a random matrix theory. Yes. Sorry, this is the logarithm of the spectral form factor. So just compute the normal modes, all the modes, and just brute force. There is no all the calculations I show are complete straightforward stuff. No, so what you can do is, first of all, you can clean up the data over certain sampling, etc. That's not difficult. But what you can do, one should really do, is plot the level spacing distribution. Should look at the level spacing distribution. It's not one of the Wigner surmise. No. So let me put it this way. Yes. Wigner answers is the real test, whether it's a random matrix theory or not. This is definitely not the real test. Yeah.
Many systems have satisfied the Wigner answer, but not the spectrum. And so you're finding an example. We should talk.
Yeah.
This is the spectral form factor just with the gas outside of it.
That's right.
There's no classical case.
No. Yes, it is the one loop around the background is completely classical. I'm never quantizing anything, doing anything to the background at all. Sorry, just doing very badly on time, but okay. Let me move on. So that I just want to say I mean, actually this is something at some point Shiraj pointed out. So I'll just also clarify this. So what happens is, if you look at this problem, there are two natural time scales. One time scale is basically the fact that there's a wall right in front of the horizon. So you can just imagine the classical light traversing time from a distance, from a radial position all the way to the wall. That should have a logarithmic divergence if epsilon goes to 0. That's an integral, right? Just over the standard dr square over dr over square root of f. And then there's another length scale, which is basically the local gravitational redshift, which is square root of 1 over square root of gtt, and that goes as 1 over epsilon raised to half. So these two, when I have this epsilon, certainly there are two quantities. One is log epsilon, one is log divergent, the other one is a power law or whatever, 1 over epsilon raised to a half divergence. And these two these two things exist. And what happens is that if you solve this problem using WKB, etc., there's a sense of localization versus non-localization, which gives rise to these two time scales. So let me give you the picture. So I'll just in view of time, let me just draw your attention to the picture right away. So if you look at these are the wave functions solved in some z coordinate. Z is related to the r coordinate. Let me not get into the details, but the point is that if you look at this here, you see that here for a fixed angular momenta, remember that we are solving the scalar field in a BTZ geometry where there's a circle, so there's an angular momentum which is a natural quantum number, and then the other quantum number arises from this boundary conditions. So when I change this n boundary condition, it starts oscillating faster and faster. So therefore, for a particular energy budget, you actually need to consider less amount of radial extent to meet that budget. So in that sense, there is a localization. On the other hand, these wave functions, these WKB wave functions, no matter how large angular momenta you consider, they change very slowly. So you actually have to integrate over the entire or a bigger range along the radial direction to meet that. Yeah. No, both of them are WKB. What I'm doing here is there are two quantum numbers. I'm holding one of them fixed, varying the other. And what this is telling us is that in one case, the wave functions are varying much more faster. So if you give me an energy, I can match that energy very quickly, staying in a very close range. That's right. Good. So you can ask, well, this seems pretty generic. I mean, I should make the statement that as long as you have a Rindler structure, a non-extremal horizon, this will be there, period. I mean, there's no, also angular momentum. This will be there for any non-extremal horizon, and therefore basically a Rindler horizon. And the time scales that I mentioned seem also pretty kinematic and universal. There seems to be no simple way to change them. But there is a way to change them if you consider sufficiently complicated geometry. So I'll just mention one case. So a long time back with these people, we were involved in some work which was completely unrelated to the discussion here. The goal there was to find out, for example, holographic dual of systems of large N gauge theories where you have large number of colors and large number of flavors. So it's much like trying to build something which looks in that sense close to QCD and so on. And then what happens there is that you can take this DP brane geometries as your UV and then start deforming it with the right deformation parameters or terms, and you find that at the infrared you get a very interesting geometry, which I'll ask you to kind of ignore for the moment. The only thing that you need to remember is that the metric functions are just some scaling functions. Good. Metric functions are just some scaling functions, and if you try to take this Q, which is measuring the back reaction parameter, it's the number of colors, number of flavors over number of colors. If you try to take this to 0, actually this is sort of a singular limit of this. So this is a non-perturbatively back reacted solution, and it's within complete supergravity and so on and so forth. The only advantage here is that this Q parameter knows about this NF over NC or NQ over N square kind of a bookkeeping. So it's sometimes called a Veneziano limit. Anyways, that's not important. What you can do is, as we just discussed, that what you can do is that well, this is the second impossible thing. Now what I'm going to do is I'm going to now impose this ad hoc boundary condition on the supergravity solution. So you might think that's completely crazy, and I kind of agree with that, because I have no clue of what mechanism I have for this geometry. But let me just assume that this is somewhat of a factorized event, and I can do that. And if I do this, then usually you will find that this dip time that we talked about in the spectral form factor, this is the time when the information whether there is a structure at the horizon scale starts reaching us. That scales as log epsilon. But usually, I mean, that would be general for any Rindler structure. But in the geometries that I just showed you, there is this additional parameter which I called Q. And in fact, there are powers of Q that can appear here, which can actually push this structure even farther away. So in that sense, this is a way to sort of, if you wish, affect the dip time. In other words, this can make your brick wall kind of approximation even better if such a situation arises. Of course, I'm not saying this is what happens in asymptotically flat space, nothing like that. I'm just trying to point out that this time scale is something that we can indeed affect. For example, if we take some UV complete theory. So now, that exactly, that is to my best understanding, that is what happens for some of the fuzzball geometries also. It's actually, yeah, that's I'm not an expert in fuzzballs, and all I know is from Nick Warner, but anyway, I think this is what exactly he was explaining. It's actually the way it happens is very interesting. But anyway, so let me talk about something again completely unrelated. Now here we were not even trying to do any of this. So this is a work. Well, I mean, I'll mention. So we have already seen. Well, for a very unrelated reason, let's imagine that we started to look at some complex geometries. By that, I do not mean any complex structure or anything of that sort. I literally mean take your coordinates, make them continue them in the analytical and in the complex domain, and see what happens. And then there is a very interesting proposal put forth by this gentleman a while back, which was a proposal to compute Schwinger-Keldysh correlation functions by essentially taking the, let's imagine that we are still in the BTZ case, RH is the horizon, but now their proposal was actually in the Schwinger-Keldysh case, you're supposed to compute the correlators on a complex time contour. They say that instead let's complexify the radial contour, and what happens is that imagine that there's a branch cut emanating from the horizon all the way to infinity. There are two copies of the fields at infinity, and what you do is you solve for, let's say, the scalar field along this continuous contour from one infinity to another infinity. And what will happen, as you can see, is that it's going to pick up some monodromy around this branch point. That was a way to compute their, if you wish, the infrared effects, and so on. I have 5 minutes, maybe. Okay, more or less. I don't. Yeah, I'm almost done. So what we started to look at was this geometry, and then it occurred to us, well, this is what there's an allowability condition that people these days talk about, which has been around for a while. Due to Kontsevich and Segal, and then Witten suggested that we can also use that condition to sort of allow or disallow certain complex geometries and so on. What does that condition mean? The condition is physically very, very simple. If I look at an action of this kind given in a curved manifold like this is a P form or a Q form field, and then you just demand that your path integral is well defined in the sense that your high energy modes are sufficiently damped. So therefore, the real part of this object, if you allow this to be complex, has to be positive, right? That's a very, very simple condition. At least we all understand that very well. At least the statement is very clear. Now, if we do that, if we take the contour that I just showed you in the previous slide and just use this condition for scalar field. For scalar field, these f's are just the scalar kinetic terms, the one forms. Then what you'll end up with is a contour like this. You find out that the region on the left side of this vertical line is actually not allowed. So what you have here is, instead of in the prescription that was put forth, what you have here is instead of one continuous contour, you have actually you have cut open the closed curve into two open curves, and then as a result you have two boundary conditions to put here and here, right? This is the work that we have in progress with Jayashish, who's around here somewhere. Okay. So it's very, very simple now. So what you can do is you can still say that, well, my infinities are still separated by this epsilon amount. That epsilon is a piece of my Schwinger-Keldysh prescription. Let me keep that separate, and let me imagine that I have a contour from infinity to all the way to this branch point or very close to it, which I denote by delta plus, and then there's delta minus, which is also very close to it but from below, and then you go from there to all the way to infinity. So again, it's just cutting it open, that's all. Now, if you are, since we are doing scalar field theory, what you can do is you can just look at the boundary term at delta plus and delta minus, and you will see that at delta plus and delta minus, because there's a horizon here, both these boundary terms diverge. They diverge logarithmically, and there are two integration constants on the upper line and the lower contour, on the upper contour and the lower contour, and I can tweak the boundary condition such that the logarithmic piece vanish. But as a result, you will see that the gluing condition, so it's like solving for the scalar field across this contour where there is a branch point sitting here. The gluing condition tells me that there's a finite jump in the momentum, which sort of looks like there's an object sitting at the horizon. So all I'm doing here is really, really simple. It's almost basic. The first line of calculus is instead, rewrite the monodromy as just two boundary conditions around the branch point. Nothing more than that. But I just find it interesting that such a thing arises, and maybe I'm close to being done. So let me give you a summary. I don't have very much to say about how one should view about these things, but at least I think the following statement is true, that we are at least designing interesting boundary conditions and so on. But what it remains to be seen, at least not clear to me at all, is how useful this is, because all that I have told you is something you already know. There is not much new in the sense that there is no new statement that was not known before. I am just recasting statements that you already know in terms of a boundary condition. This might be a useful way to think about dynamics, but anyway, it remains to be seen. And of course, a microscopic understanding of this, whether it is justified or it should be outright rejected, is also a good question, and so on and so forth. But I did not tell you my actual motivation for doing this. I really wanted to study something else. I wanted to study quantum field theory in ADS for a completely different reason. And that you can study from various points of view. One way to do it is actually take a hyperbolic lattice and put spins on it and take the continuum limit, which will give you a quantum field theory in ADS. That's where I really want to get into or go into, and these boundary conditions I hope are going to be useful. So as I said, to quote some wonderful thing, these are my principles, but if you don't like them, I have others. So thank you. Yes, please. Yes.
Without jets working so hard that they would expend their fuel here.
Yes.
So isn't it a very unphysical boundary condition?
It is. So the point is that so there are sort of cop-out answers to this. One very simple cop-out answer, which I don't really know how else to, I don't like it at all in some sense, that if you imagine exotic matter, maybe they do it. But let's leave that aside. What actually people in fuzzball do Yes, yes, yes. Yeah, it has to be something that we have never seen.
Very straight.
Absolutely true. But I think what the more detailed fuzzball constructions give you are a bit more interesting ways of doing this. So what they do is, first of all, they don't have this non-extremal horizon. They have extremal horizon, but nonetheless, there I think there's a mechanism, because you are in 10 dimension and whatever, and you have branes and fluxes. There are fluxes that can stop you from collapsing. So the fluxes are in the internal directions and so on. So this is very complicated and somewhat fine-tuned perhaps configurations. Maybe fine-tuned is not the right word, but at least there's a class of ways of doing this. So that I find is more interesting. But yeah, yes, that's the only answer, I think, reasonable answer I can think of.
Arnab,
Yeah.
questions. I was trying to think of how one could go about distinguishing this picture from the usual picture of the black hole that we have. So, there is the thermal one-point function conformal theories that one can compute, and can use holography to argue that it behaves in a certain way with respect to its conformal dimension, right? Where you see the time all the way to the singularity. In that, there's an oscillatory behavior with the exponent being the time to the singularity. Okay, but if you use this picture instead, you would have a different prediction, I would imagine.
That's right. That is right.
So then that's a clear
contradiction,
distinction between the two pictures.
That I agree.
So then one can see how conformal field theory behaves.
I agree.
To see which one is correct, right?
Yes, I agree completely.
Thank you.
So in that graph that you showed for the spectral form factor or log of it, you said that there's a behavior which is like chaotic e to the minus.
The Plato value, yes.
Yes. Oh, so that's what my question was. It's near the Plato value where you see that behavior, like where in
the chaotic, the true sign of chaos is when the ramp starts happening, and then in the details of that. The Plato is sort of a kinematic region. It will happen for pretty much any system.
So in the Plato region, we see that e to the minus.
Yes, that is exponentially suppressed because of some kinematic reason. It will happen for any system, not just.
Okay, thank you.
Any other questions? Okay, then let's thank Arnab again.
Okay, this will start working, right?
Yeah, sure.
For the full screen comms.
Go back.
Maybe you can.
We want to continue set of live captions. So, data ভিতরে শিফট করে পড়ব মানে এটা হচ্ছে এমনি এটা তো এটা হচ্ছে এটা টকটা তো সে চাହୁଁଛନ୍ତି যেତେବେଳେ আছে সেটা চেঞ্জ করে দেয় এটা মারবে বাকি সব ক্লিয়ার করে দেবে দিরা বলবো
Okay, so the next speaker and the last speaker of this session is Blaise Gautreau, and he'll be telling us about near extremal holographic coordinates.
Thanks a lot for the introduction. Thanks for the opportunity to tell you a little bit about these results. I'm very happy to be here. It's been a great stay. So this is work that I've done in collaboration with a few people at École Polytechnique. David Ramirez, who is currently a postdoc at Polytechnique, Michael Sanchez Carrito-Anandia, who is a postdoc who has now moved to Dublin, and Clément Supio, who is my PhD student in year 3. Yeah, is that okay? Should I bring this up a little bit? So Clément Supio, who is a PhD student with me at École Polytechnique as well. This is also based, so this is on a recent preprint on the archive from a few months back. There's ongoing work with the same collaborators, and some of the results are also based on a previous paper with different collaborators. Let me start with some introduction and some motivation. There are very large families of holographic theories whose charged black hole solutions have an emergent geometry when you take the near extremal limit and when you zoom close to the horizon, which takes a very simple form of a product of the two-dimensional anti-de Sitter spacetime with a simple space, a d-dimensional simple space like a sphere or a plane or a hyperbolic plane. And in these kind of black hole spacetimes, then there are a certain number of properties of the full spacetime that can be deduced just by knowing about this near extremal geometry. In particular, how various thermodynamic quantities like the entropy density and the energy, etc., deviate from their value at extremality. This can be captured by Klein reducing the spatial dimensions and just working with an effective theory that only captures the ADS2 part of the spacetime. Another reason to be interested in these near ADS2 spacetimes is the recent evidence for a duality in zero spatial dimensions. So you just keep the radial coordinate and time between near extremal ADS2 and SYK models. And this, one of the ways that you can see that this duality emerges is because there's a universal sector, a universal effective theory that describes these dynamics, the SYK dynamics in the limit of low temperatures or large coupling, and the gravitational dynamics in this near extremal limit where ADS2 emerges. And this effective theory rests on an emergent invariance of the time reparameterization, which happens to be pseudo-spontaneously broken down by the state, by the ADS2 metric itself, down to a smaller group, which is the global SL2R symmetry. Sorry, this is not coming out right. And this universal sector is described by an action which is pretty simple. That's the so-called Schwarzian action. C here is the length scale, it's a coefficient. And this is simply the Schwarzian derivative between these functions of time and tau. However, the question that I'm interested in is what happens when you put space back in, when you don't consider pure ADS2, but again, thinking back about these higher dimensional systems, what happens when d, little d, is non-zero. In fact, we know that the effective theory, when you put space back, has to be different from that Schwarzian theory. Or at least there has to be more. There's a general statement that at finite temperature for interacting systems, if you go to sufficiently low energy, long distances, late times, then the effective theory is hydrodynamics. And in fact, away from extremality, so now I'm thinking about some high temperature regime, and for frequencies wave number is small compared to temperature, we know since already a few years that the low energy dynamics of charged black holes is described by hydrodynamics. So that means conservation of the stress energy tensor and conservation of the current. There's an underlying assumption that there's a notion of thermal local equilibrium, and this underlying assumption through a well-known procedure is what allows you to write so-called constitutive relations for these objects, for the stress energy tensor and the current, allowing you to close that system of equations and solve it and work out what's the spectrum of collective excitations, the late time dynamics, and so on and so forth. So when you go through this algorithm, what you find out is that the retarded Green's functions, which are the objects of interest here, display so-called hydrodynamic poles. Those hydrodynamic poles are poles that have a dispersion relation, so frequency as a function of wave number, that vanishes at zero wave number. The fact that these poles go to the origin of the complex plane is directly related to the fact that they are poles that correspond to conservation laws for global symmetries of the state. And the more common ones that we encounter are, for instance, for a charged fluid, so longitudinal sound, where there's a real part that starts linear in k, and then some attenuation, which is imaginary at order k squared. But we will also find longitudinal thermal diffusion. Longitudinal means in the same direction that I've picked for the wave number, and transverse momentum diffusion. Now the question that I want to ask is, what happens when you consider the near extremal limits? So temperatures that are going to be small compared to the inverse extremal radius. We already know a little bit what might be going on. In particular, so here I'm taking an example drawn from SYK, and this is a chain of SYK models. So you just put a chain of them, and then you put some hopping terms between the different SYK dots, and if you do that, then you restore some notion of space. And this is a one-dimensional chain. This was studied a few years back by Gu and collaborators. And in those systems, you can compute an object that I will call the IR retarded Green's function for energy. This is an IR retarded Green's function because it doesn't capture all of the dynamics of those systems. It only captures the dynamics in a restricted sense that I'm going to try and make clear as I go along in the talk. So if you stare at that expression, you'll see that there's a diffusion pole, a thermal diffusion pole, exactly like I was showing you on the previous slide. And if you, and then there's some structure in the numerator. And in particular, that structure, the fact that there are these zeros here at omega equals plus or minus I2 pi t, this is directly controlled by the emergent SL2R invariance of the Schwarzian theory. So this is how the L equals plus or minus 1 generators of SL2R manifest themselves in print. This is the imprint of these generators on the retarded Green's function. There's an issue though. Like I said, this is an infrared retarded Green's function, so you have to take a special limit. This is the retarded Green's function that you compute within that Schwarzian theory that you slightly extend in space. And there's a very clear way how you do that when you solve the SYK theory. And in fact, when you compute the full retarded Green's function, which you can do in certain limit, this was done by Choi and collaborators a few years back, you get a much more complicated expression. You can plot out what are the zeros, what are the poles. So here I've only plotted out the poles. This is the imaginary part of frequency. This is the wave number. And this is the same diffusion pole that's captured by the infrared retarded Green's function. So that feature is there. But if you look at the zeros, you don't find at all zeros located at plus or minus I2 pi t. So there's some scrambling going on between this IR object that you compute within the spatially extended Schwarzian theory and the full retarded Green's function that you compute using your 1D SYK chain Hamiltonian. There's a similar thing going on in holography, which is what we had discussed back in that paper. I'm not showing the plot. It looks very similar to that one, and the results are extremely similar. So, in other words, the Schwarzian is not quite enough. There's other things going on. Yeah. This one.
You can consider generalization of this chain where the the interaction between the sides, it's actually all to all, but it falls off polynomially.
Sure.
It's solvable. And if you take the fall off to be slow enough, at some point in the denominator, this power of k, it becomes fractional. So would it be correct to say that for such systems you do not have a hydrodynamic regime, or how should one?
I don't know. Why don't we talk about it after, because I don't know those results, so I can't really comment. Yeah. Can I go back to that question later? Because I think I might be able to answer it more clearly in a few slides. Sure. Okay, so now if let's look a little bit at, so this is the same as this, but flipped the other way around, because I usually plot minus the imaginary part of the frequency divided by 2 pi t. And if we look a little bit what's going on here, besides the hydrodynamic pole, there's also this tower of gap poles. So these poles are spaced out at integer multiples of the frequency, and their specific location on this vertical axis depends on the scaling dimension of the least irrelevant operator in the SL2R theory, in the Schwarzian theory. And this is something that has been computed in many different instances in holography, and it's a well-known feature of the spectrum. What is also well-known is that when you take the t to 0 limit in those IR retarded Green's functions, then all of these finite temperature poles coalesce into a branch cut. And this is a limit that you can take very explicitly in the retarded Green's function that you compute. And you see a branch cut coming out, which is a power of frequency controlled by this IR scaling dimension. Now, surprisingly, besides that branch cut, you will also find that there is a gapless mode that survives at 0 temperature with a dispersion relation whose leading contribution at k² is the naive 0 temperature limit of the corresponding
hydrodynamic diffusivity. This makes no sense a priori because you're completely outside the regime of hydrodynamics. So you have no cause to expect that the gapless mode should remain. Another thing that should worry you is I've just told you that there's a branch cut that appears on the negative frequency imaginary axis. But now I'm also telling you that for some reason there's a pole there. So mathematically something is not very well defined.
The lowest branch there, the one that's shaded in orange, is that coming from some mode of the graviton?
This, yeah. But also from other sectors, depending on which sector you're looking at. Okay, so a few puzzles and questions. What do we really mean by this IR retarded Green's function? Because that means that somehow we're measuring retarded Green's functions at the boundary of ADS2 cos R2, but we're also deforming it away from extremality. So there are modes that are blowing up. So it's not exactly clear what the status of this kind of object should be in the dual field theory. Another question that I've tried to tell you a little bit about is to what extent those near extremal dynamics are controlled by the Schwarzian effective theory, or let's put it, or more precisely, how does it imprint itself on the full UV retarded Green's function? And we see that some features survive and some do not. More broadly, could we formulate some sort of near extremal fluid gravity construction that would capture not just the hydrodynamic modes, but also these extra modes that originate from the Schwarzian, but now these are gapped, so it's not going to be exactly the same as a fluid gravity construction. And further, so coming back to this issue of zero temperature gapless modes, there should be some sort of symmetry, some emergent symmetry that justifies their existence. Because whenever we encounter this in other situations, such as fermiliquids and superfluids, there is some emergent global symmetry that protects zero temperature gapless modes. And here, I don't quite know what that is. Okay, so in this talk, what will I do? I'll give you analytical expressions for the current and the shear retarded Green's function in some special cases. Two planar black hole spacetimes that have a near extremal ADS2 cos RD R2 work in two spatial dimensions geometry. I'll do that using a matching calculation that extends what people had done in previous literature. The irrelevant deformations away from ADS2 will play an essential role. And what those expressions will do is they will capture the dynamics of the hydrodynamic poles, but also they will catch that tower of gap poles and how these two sectors interact with one another in interesting ways. Yeah. I will answer that question. So this is a little bit of a technical slide to show you what I'm doing. I'm having a 3+1 bottom and holographic action with gravity, negative cosmological constant, charge, and some massless scalars. The only purpose of these massless scalars are to support analytical black hole solutions. So that makes my job easier in doing analytical calculations. And I can take a near extremal limit by changing coordinates from R to zeta, and then taking a small epsilon limit that zoom near the horizon while zooming the outer event horizon close to the extremal limit. So when you insert those changes of coordinates, so there's also a rescaling of time, inside this metric, you take the epsilon to zero limit, you'll find that the geometry becomes a black hole in ADS2 cos R2 plus irrelevant deformations that you can compute order by order in epsilon. I'll give you 5 seconds to finish staring at this. You won't play much of a role in the rest of the talk. These details, for instance, where there's an R0 when there's an RE, that doesn't really matter, but okay. That's just to show the kind of spacetimes that I'm using. So these are neutral scalars, which are massless, so okay, they have issues. The only reason why I'm using them is because they give me another example of an analytically known spacetime, which has an ADS2 cos R2. Yes, that doesn't really play a role in what I'm going to say, but you're right. In principle, they break translations.
Yeah. What I will use those solutions for is to compute the current retarded Green's function at zero density. So I'm really just using this as a background. I'm not coupling the perturbations of the metric or of the scalars to those of the gauge field for that particular calculation. So the fact that they're breaking translations really plays no role in the calculation I'm showing. This is the second technical slide. How are we doing that calculation? Well, in both of these two cases we're looking at, there's a decoupled equation for the bulk perturbations. Here I'm showing the equation for this translation breaking black hole that Loga was asking about. This is a perturbation equation in terms of the bulk electric field. It can be put under a semi-nice form. And what we do is we're going to solve it, since we can't solve it exactly for any value of frequency and wave number and R, we're going to solve it in two different regions that have some overlap. We're going to solve it in some outer region where the geometry is nearly ADS4 with some temperature corrections. And that region we define in such a way. This can be shown by just staring at balancing out various terms in that equation. So essentially, if I can always find frequencies and wave numbers sufficiently small that this condition is met, then I define an inner region where I zoom close to the near extremal horizon that's given by another condition. And those two conditions are compatible with one another, so I can put them together and I can find some non-trivial overlap region where I can glue those two solutions together and do the matching. So that's what we do. And we do this order by order in epsilon, where epsilon is this expansion parameter, by appropriately scaling the frequency, the wave number with epsilon and the temperature as well, and imposing ingoing boundary conditions on the inner solution. So that's as much as I'll say about how we do this due to the lack of time, but I'm happy to give you more details if you're interested. So what do we get out of this? We read off the retarded Green's function here at the ADS4 boundary by having appropriately glued that outer solution to an inner solution and imposing ingoing boundary conditions. This is the denominator of the retarded Green's function that we get. And so if we want to solve for the poles, we just want to equate that to 0 and find the solutions of omega as a function of k for various values of the temperature. Here I'm working with dimensionless quantities where omega, k, and t are scaled by the extremal radius. I'm plotting imaginary part absolute value of omega over 2 pi t divided by k, divided by 2 pi t on the vertical axis, and this is k over t on the horizontal axis. There are some, here you see there's some structure in this expression. There are analytical contributions, omega, k squared, and so on. And then there are non-analytical contributions which are hidden in this calligraphic G. And these play an important role. These non-analyticities, in fact, are exactly what is enabling us to capture those gapped poles coming from SL2R, which you can convince yourself of by working out where are the zeros, where are the poles, sorry, of these non-analytic contributions. This is coming at order 1 in epsilon. So in order to catch that behavior, we do need to keep track of irrelevant deformations away from pure ADS to cos R2. So these order epsilon terms here in the metric that I didn't write, but that you can work out order by order. So let's break down a little bit what's going on here. So there's a first region, which is the hydrodynamic region, where frequencies and wave numbers are small compared to temperature. And you can expand this order by order in K and work out what is the expression for the hydrodynamic diffusion pole. This is a charged diffusion pole. And it has some quadratic piece and a quartic piece. And this expansion in K squared has a radius of convergence that you can work out explicitly in this case, which is where there's a collision that happens with the first gapped pole. And this is happening at frequencies over the temperature, which is maybe the thing that you would expect in terms of the regime of validity of hydrodynamics. This is controlled by temperature, tells you about typical collision scale if you have a system of particles. And perhaps more surprisingly, a difference with non-extremal spacetimes is that now the radius of convergence of the wave number is not given by t, but by square root of t over r. So this is enhanced. In particular, you see that here, the first collision is happening at values of k over t, which are 50-ish. That number changes as you lower the temperature, it gets bigger. So it's not controlled by t, but square root of t over RE. You can see that there was a question whether this hydrodynamic pole would be continuously connected to the zero temperature pole. Here you see, for instance, that there's a log t that will diverge as t goes to 0. So obviously, it is not going to be, this is a sign that it's not going to be continuously connected. Another sign are, sorry, before I go there, so we also have all of these gapped IR poles. Again, they're at frequencies controlled by the scaling dimension of the IR operator, which for this particular state is like this, goes to 1 as k goes to 0, so you can count, gives you 2 pi t, 2 pi t, 4 pi t, 6 pi t, and so on. And those poles, in fact, can be deduced from something that's very close to this IR retarded Green's function I was discussing before that you can work out in that particular case. And it's this one-on ratio of gamma functions. And if you ask, where is this having poles? Those are the zeros of this gamma function, and they give you that power. But again, that's an object, it's a separate object that you compute purely in the ADS2 cos R2 geometry. So it doesn't quite do the job that it doesn't give you, it doesn't tell you about this matching. Whereas the expression we get does tell you about how things match up between the IR theory and the UV theory. Okay? So hydro breaks down here when there's a collision with the first gapped mode. And in fact, what happens is that those two modes collide with one another. They pick out a real part, go off in the complex plane, come back down on the imaginary part, on the imaginary axis, and the pattern repeats. So let me illustrate that a little bit with a movie just so you can see what's going on somewhat better. So this is the complex plane, imaginary part of frequency, real part of frequency. The hydrodynamic pole is sitting here very close to the origin at small values of the wave number. These are the gapped poles in blue, in white. And this is for some low value of the temperature. So let's start the movie. So you can see here the hydrodynamic mode is going down on the imaginary axis, getting closer to the first gap pole. They collide, move off axis, recombine. There's another collision, a recombination, a third collision, and then we're done. Then no more collisions. So this pattern of collisions repeats a couple times, and then eventually the poles don't recombine anymore, and there are two poles that remain off axis with the real part. Those are the finite temperature analog, the small temperature analogs of our zero temperature gapless modes. So in fact, what's going on is that this hydrodynamic pole, in order to move off axis, has to snatch one of the poles of this SL2R tower in order to get a partner and move off axis. That's what we're seeing here. You can see also that those white dots, they're moving up by one level. That's because of this snatching thing. SL2R fixes the spectrum on both ends of the plot that we had. And so if one of these poles gets snatched by the hydro pole, then another one has to come up in order to fill its spot. So that's what you're seeing with these white dots going to the gray dots. This, you can think, it's a little bit like a billiard, right? You have these balls and then they collide, and the collisions here are such that they move away along this cone, but at some point they move away too far from the imaginary axis in order to be able to recombine. We'll see that it does not always happen like this, but let me go on with the talk. Okay. So all of these poles that you see here, they remain purely imaginary, and they just go down by one level when they cross the other poles that have moved off. So in this region, this is almost zero temperature. So what you can see is that taking the zero temperature limit from this calligraphic G that had the digamma function, then you find the logarithmic branch cut that appears. That's the same branch cut that we discussed earlier on. And what that does when you solve for the modes is that you find that the mode picks up a real part and also some non-analytic pieces. Again, a signature of the fact that this is a regime that has nothing to do with hydrodynamics, where everything should have
remained analytic. And that gives a resolution to that question that we had before. How can there be both a pole and a cut on the negative imaginary axis? Well, the answer is that there is no pole on the negative imaginary axis. You just need to go sufficiently far in your calculation in order to see those non-analyticities and the associated real part coming from deciding on which side of the cut you are. So that was for charge diffusion. Let's now look at the case of transverse diffusion in the Reisner-Nordström ADS4 black hole. So now again, I have some expression for the denominator of the retarded Green's function. There are similarities, analytical terms, and non-analytical pieces, and coefficients differ. They're not too important. The overall dynamics is very similar to what we've seen. So there's, again, a hydrodynamic mode with some finite radius of convergence, which is root T over Re in K. And then there are some collisions here with gap holes. But if you close up a little bit on those collisions, so here I'm showing you close-ups of these two regions here, now you find that there is no actual collision for real values of the momentum. Those collisions are happening for imaginary values of K, and so for real values of K, they just appear as these avoided crossings. So here there's a gap which is proportional to temperature. So in the same, if you want to think about it, in terms of these collisions, now this is the hydro mode, there's the SL2R mode, this is going down, and then as it's getting close, there's some sort of repulsive effect. And then this pole stops, and that pole goes down, goes to the next, stops. So these are like, these magnets with poles, north-north, south-south, and so they're pushing one another down the imaginary axis. That's what you're seeing here. What's the difference? The difference has to do with what is the dimension of this IR operator. In the case of charge that we discussed before, delta was 1 plus some order k-squared piece. And that meant that the IR retarded Green's function at order epsilon had some k dependence, and the non-analytic pieces were multiplied by k-squared here. On the other hand, for Reisner-Nordström, this delta of k is different, but its expression is known, and when you expand it for small k, it's 1 plus order k to the 4, there's no k-squared piece. So now the inner solution at order epsilon remains k independent, it only depends on frequency, and that manifests itself as an omega here, multiplying the non-analytic piece. So here we had k squared, here we had omega. This is the essential difference between these two dynamics. So it really has to do with the details of what the IR scaling dimension is for each case. And similarly, we can take a zero temperature limit, the gamma function as a cut, and the poles move off the real axis in exactly the same way that it did for the charge. But this only happens at exactly zero temperature, because at any finite temperature, the poles remain purely imaginary. I'll finish. I'm done. So this is what we've done. Some subleading order matching that resolves not just hydrodynamic poles, but also gapped poles and how they interact with one another. We applied it to two cases, the current retarded Green's function and to the shear sector of Reisner-Nordström. So the obvious next steps would be to try to extend this to the longitudinal sector and energy diffusion, for instance. There's still a question mark on exactly why we find zero temperature gapless pole. There's definitely some relation to the fact that there's ground state entropy, but precisely how that works is not clear. It's clear for shear, because then the diffusivity is eta, the shear viscosity, and eta is S. So the fact that it survives at zero temperature seems to be well connected. But for charge, the diffusivity is not obviously related to the entropy density. So that argument doesn't go through directly. So there's something more to understand than just saying something about ground state entropy. It would be nice to do this off-shell, so we can actually write an effective theory that would couple these modes to the appropriate spatial extension of the Schwarzschild. And another direction would be to compute fluctuation effects on these hydrodynamics due to the Schwarzschild, which is something that can be done thanks to work by other people that I'm not mentioning here. Thanks very much.
Also hope that online you develop a kind of hydrodynamics by taking the modes and coupling them to the spatially extended Shortfield. But then I thought you said that somehow the Shortfield theory was not correctly capturing these poles as frequencies of order temperature.
That is, it's capturing them. It's capturing them, but it doesn't capture how they interact with the hydrodynamic degrees of freedom. And so what you need to figure out is, how do they couple? How does this coupling, how do you write that coupling at the level of an effective action?
Since the Shortfield rises due to time reparameterization, just thinking in terms of symmetry should give us the coupling, do you think, or not? I mean, that's how it works with, you know, other modes in the bulk that you can just through time reparameterization.
Not sure. I think until one does the calculation, it's not entirely clear what will happen.
Sorry, two questions. First, the square root t for the is that because the imaginary part of the diffusive thing goes like k square, so that k square then becomes t? Is that the reason?
Yeah. So if you want to work that out, you take this, which approximate very well the dynamics all the way to here, and you equate that to that frequency, and then you get your square root.
Okay. Second question: is in the limit that the temperature goes to 0, is the residue of the hydrodynamic pole parametrically larger than the residue of all the other poles?
This I need to compute. I don't know.
Thank
I
you.
haven't checked. But I told you, I think, that the residue of the other poles is going like T, so yeah.
So this one stays fixed. Right?
Yes, I believe so. It has to. Otherwise,
so
it would.
special. Like it's more
Yes, yes. So it must be protected by something. And it would be nice to be able to say precisely what something is.
Quick question, Blaise. Just wanted to understand this matching that you have done, because you are doing it on a region. Like, how exactly do you do it? Like,
I'm doing what?
The matching that you are implementing to compute the solutions. You are implementing it in a region rather than on a slice or something.
On a hypersurface.
On a hypersurface. Okay.
Which you can think of as the boundary of the ADS
Okay. Okay. So I got confused. I thought, how are you going to implement it on a region? Okay.
No,
Thank you.
You implement it at a special slice that you pick.
So it's very nice, interesting talk. So this cutoff that you use for the infrared thing, that usually where this Schwarzian theory is an effective description. So that is supposed to be of the order of like a temperature, because that comes from a specific heat, right? Specific heat times temperature, this phi dialectron value of the, but then when you take the T goes to 0 limit, that cutoff. So I'm saying that if you think of the mixing of the Schwarzian with the hydrodynamic
My
modes.
theory is not T, it's 1 over the extremal radius. So it's mu, the chemical potential, if you like.
Yes, so this is what is confusing, because usually it is said that like the 2D work says that there's a near horizon cutoff, and this comes from, I mean, when they talk of this, like how your extremal black holes are modified, like this density of states is modified in the partition function calculation of Turiachi and all. The contribution mainly comes from this cutoff that is given by the specific heat and like the black hole thermodynamics. So. But in your case, you're saying it is there is this other scale that
cutoff. Yeah, right. There are 2 scales in that problem that we need to disentangle. One scale is 1 over the extremal radius. So that this defines the near extremal region. But then there's that scale C, which is the one you're thinking of. This C here appears in the entropy density, which is the entropy density is S0, the value at extremality, plus some number
specific heat times T. Yeah.
And so then you can define another temperature scale, 1 over C, where quantum fluctuations from the Schwarzian become important.
I see, I see. So you say that this hydrodynamics is controlled by mu and the other is this 1 over c scale. So there are two scales in the problem.
You can think of it as there is some hierarchy where 1 over c is small compared to t, small compared to mu.
I see.
And that works out because you want t less than mu to be in this near extremal region. And 1 over c less than t works because you ask that the ADS radius is large compared to the Planck length, and because you want to be in this hydrodynamic regime, which sets a bound on how small your transverse space can be. And that brings C down.
I see.
So we're not in this regime. When I say zero temperature, you can think of this as I still have 1 over C much less than T. So I'm not probing that regime. That's the next paper.
Sorry, one more. This is a vague and general question. You have all these massless modes coming down to zero temperature. Why don't they contribute? Why is the contribution of the Schwarzian to the free energy, to the determinant, more important than the contribution of all these other modes?
But these modes, they are the Schwarzian at non-zero temperature. So if I go back here, if I go back to this expression, how do you get that expression? You start from the expression, the two-point function in the Schwarzian theory for an operator of dimension delta. So that goes like 1 over tau to the 2 delta. Then you do a conformal transformation to put this at finite temperature. This gives you 1 over sinh to the 2 tau. And then you do a Fourier transform. Then you analytically continue back to Lorentzian time, do a Fourier transform, and you'll find the gamma functions. So those poles are precisely how the Schwarzian theory manifests itself in the spectrum at finite temperature.
So these poles have various different values of k that all are...
The values of k is different. That's non-Schwarzian in a sense. Or that's taking this Schwarzian calculation, which has no k, and just substituting delta by delta of k.
Right. So is the point that for a black hole, there's a sphere, and so k is like a gapped spectrum, and so the lowest one is the most important one?
You would have to, you'd have to compare how that k is with the radius of the sphere.
Okay, so there's only one really light mode in a black hole. I'm trying to understand because I hear people tell me that the Schwarzian gives the dominant contribution. The Schwarzian is zero mode on the sphere, right?
Mm-hmm.
And I'm trying to understand why these other modes don't also contribute a lot. Not the gapped ones. These Ks, yeah. Just for the determinant. Maybe it's probably a stupid question, but maybe Ashok.
I'm not sure how to answer you.
Is Ashok to you?
Precisely.
And that's because the black hole is on a sphere, so this K is like...
Yeah.
Yeah.
Yes.
So to log T, the Schwarzian modes are the only contributors. Right?
Because these are all gapped.
Exactly. Yeah. Yeah. They are gapped by the inverse radius of the ADS of the sphere. Yeah. 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 Then there will be the extra zero modes. Yeah. Yeah.
Yes. And here, this is what we're doing.
Yes, exactly. So with the determinant now,
Yeah.
will you get more than the Schwarzian contribution?
I don't know. I've not done that calculation.
But what do you expect?
Well, maybe. Someone
Okay.
should do that calculation and check it.
Yeah, maybe we should wrap up and
Okay, I have a couple of announcements before we wrap up. Thanks, Blaise. Yeah. So for participants going to the Konark excursion, particularly the foreign participants, I think we need your passports to basically show there. So we'll leave here around 2 and then go by the guest house. If you do not have the passport, you can pick it up and then we'll leave. Okay. And I think for Indian participants for online, they are asking for some ID. But I think you can, if there are a few people who do not have any ID, they can just buy it there from the ticket counter. Don't buy the ID, but you can buy the tickets from there. Okay. Okay. And for those who are not going for the excursions, there is also buses. The timetable I have given already in the mail.
আজকে কিছু প্রোগ্রাম আছে
we will go.